When you turn off the volume here, like, yeah, it's
Yeah.
on.
Like on one of the
You check and spending once in a while.
Yeah.
Hello, good morning, everybody. How's the volume? Are we okay? All good? Brilliant. My name's Duncan Rigg. I'm here from Sonardyne. We're based in the UK, and we're going to spend a bit of time this morning talking about USBL optimization, so subsea positioning, some of the other advantages of these systems. And the idea is that try and give you guys a bit of confidence about the best way to set these systems up. This is very much focused on Sonardyne's offering, but a lot of the stuff we're going to talk about is completely applicable across the board to lots of other vendors' USBL systems as well. Quick introduction to myself. So I did a degree in ocean science from Plymouth University. I went straight offshore working as a technician, integrating sensors onto ROVs for pipeline, jacket inspection, that type of thing. I did 5 years doing that, got very bored of just watching the seabed, so I decided to go and get a proper job working at Sonardyne, where I was offshore installing, commissioning, calibrating a lot of the systems, particularly USBL systems. So I've been there, I've done it, I fully understand the pressures that get associated with this type of equipment, and how important it is as a vendor, we make them as simple and straightforward to use as possible. Okay, so what is a USBL system? I'm going to do a quick sort of overview of how these systems work. I think it's quite important to understand how they actually work before we can start sort of going into fine-tuning them a little bit. But I think this picture sort of summarizes what a USBL system is. I think the best way to describe it is it's a gateway. Yes, it's doing some positioning, but it's also a gateway for data as well. So if you want to get data back from the subsea environment up to the surface, you can use your USBL system. And they've got lots and lots of applications, from deploying beacons that sit on the seabed for decades, and you don't want to be able to touch them. You need to make sure you don't move them so that they do operate correctly and you get good data from them. To very shallow water coastal operations as well. These systems need to be able to do all of that. And because of that, there's lots and lots of ways you can adjust them, you can tune them, you can pick different types of hardware. So it really does depend on the application. So how do they work? So our transceivers consist of we call it the transceiver. Other vendors call it something slightly different. This is the bit that's transmitting the acoustic pings. So we have a transceiver that you deploy on the end of a pole, a nice strong rigid pole, and that needs to be deployed through the hull or over the side of the vessel into a nice clean environment. And by clean, I mean no air, reduced noise. And how does it work? Well, we have a number of elements in the transceiver. One's a transmit element. So that's sending the interrogation. That sends out a signal to anything that's underwater and says, "Where are you?" That underwater beacon then sends a reply back, which is detected by the receive elements. And what we're doing is we're basically measuring time. These systems depend completely on time. They're really, really accurate. The accuracy of the system really depends on how well it can measure time. That's what it comes down to. So the first thing we're doing is we're measuring slant range. So this is the distance. And we do that just purely by measuring how long it takes for a signal to go down and come back again. We know how fast acoustic signals travel through water. We can work out the distance. The next thing is the azimuth, the angle it's coming in at. Again, we know exactly where these transducer arrays are. We've got 5 of them here, the blue ones. As the signal propagates across, they all trigger at different times. That then allows us to work out the angle that it's coming at. And the next thing we want to know is the elevation. So at what angle is the signal coming in at? And again, all we're doing is we're using timing. But we're also doing something quite clever there as well, where we're looking at which part of the acoustic signal is being detected. Right, so some considerations. I think this is probably the first thing you want to think about when you're talking about USBL systems is what's it going to be used for? That's question number one. What's the system going to be used for? I think I've got some good examples up here. So ROV tracking, that's the bread and butter of these systems. Depending on the size of the ROV and what it's doing, you might want to have a slightly more deep water rated system, or you might want to have a system that's suited for shallow water. Getting data back from the seabed, as we mentioned earlier, lots of different applications there. These systems are basically modems. DP, I think this is one of the biggest sort of grey areas with these systems. Does it sit with the vessel crew when it's interfacing the DP system, or is it a scientific instrument? I think, again, we get a lot of questions about being able to, excuse me, do something with the system, but they don't want to interfere with it because it's part of the DP system. So there's some things around that you can do. And in more recent times, AUVs. So the one you can see there in the middle, that's from the National Oceanography Centre in Southampton. That is actually boating with boat face. That's the real boating with boat face. So yeah, make sure you know what you want to do with the system. And the next thing is deployment. It's probably the most critical part of getting the system to work correctly. It really is. And that video there, you couldn't really see it very much, but there was a little bit of movement there. Very, very slight amount of movement. But that vibration was preventing the system from working correctly. The deployment is, without doubt, the number one source of issues that we come across. People have used scaffold poles. They've put broom handles even, and they deploy these systems over the side of the vessel, and they wonder why, when it's flapping around and bouncing around, why it's not operating correctly. You've got to have the right sort of deployment. And in reality, it's got to be better than you expect it to be. Like you've got to engineer in a decent factor of wiggle room, basically. So we do deployment systems, but these have been designed specifically to withstand sort of 15 knots of current. That's kind of where we sit with our deployment systems. And where it's on, where you're going to deploy it on the vessel is also really critical. I mean, if we're talking about research vessels, they tend to be very, very quiet compared to a lot of other vessels for obvious reasons. However, if you go and stick your USBL right next to one of the thrusters, it's just not going to work. So placement on the vessel is critical as well. And the next thing to talk about really is noise modeling. So we can get a really good, we can decide which USBL system we want. We can get a good deployment solution. We can put it in the right place on the vessel. Then we need to think about what's going underwater, the bit that we're going to be trying to talk to. So we can do some modeling on how these systems are going to perform based on the equipment that's chosen. And one really basic but good example is, do you go for an omnidirectional or a directional beacon? These are two standard choices. Yeah, omnidirectional sends a signal out in every single direction. But what that means is the power that it's transmitting is distributed 360 degrees. A directional beacon sends all that energy in one direction. And what that means is you could, if you wanted to, prolong the battery life of a beacon by not transmitting at such a powerful level, but just focusing it in one direction. So for DP, for dynamic positioning applications, they tend to go for the beacon you can see there on the right-hand side. That sits on the seabed and it just sends a signal back up to the surface. Doesn't distribute energy anywhere else. ROVs, on the other hand, might want to be maneuvering around a little bit, go for an omnidirectional. So again, choosing the correct hardware for the job is really, really important. But one thing I would suggest to anyone that's in a situation of looking at USBL systems and acquiring a USBL system, come and chat to us, because we can model up how a system will perform. And in that model, we can look at not just the hardware, but where it's located on the vessel, noise sources, tilting the transceiver even. There's lots of things around it we can do. But it should just give you a bit more reassurance that the system's going to perform to the level you want it to. And I mentioned that these systems aren't just for underwater positioning. There's lots more they can do. So one of the things that I think is absolutely incredible is the ranges we're now able to achieve with these systems. So this And this on the right hand side there, you can see the S value. That's slant range. That's 10,687 meters. So we actually got to beyond 11 kilometers distance from the vessel to the beacon, and it's all well and good saying we can track at 11 kilometers, but if the beacon position's bouncing around all over the place, it's useless. But we're in a 20-meter cluster at 11 kilometers. So that was, I think that's absolutely mind blowing. And that was on one of the Woods Hole vessels. We ran that experiment. So yeah, you can go super long range if you want to. It's very, very niche, but some people do need to go that far. But yeah, you can also go very short range as well. Another system to factor in that complements the acoustic system really well is inertial systems. So inertial systems and acoustic systems marry up very, very well. The acoustic system has sort of got an update rate that's relatively slow. Once every few seconds, you're getting an update. And you might get a few where you miss an update. So you might have a period of, say, 10 seconds where you haven't had an update at all. But an inertial system will fill in those gaps. And the inertial system, although very, very accurate, will drift over time. But the acoustic system prevents that. So they are the perfect marriage made in heaven. And there's lots of other benefits about improving battery life as well when you're using inertial systems. It's definitely something to think about. Inertial systems also aren't just for subsea vehicles. We can put them on the vessel as well. We've already sort of mentioned a bit about the transponder choice. But yeah, you can go omni, you can go directional, you can go for very small beacons if you put them on divers or small observation class ROVs. You can go for very, very long duration, big battery pack units as well, if you haven't got any battery power going down to your vehicle, or if it's going to be sitting on the seabed. So we do some units that are designed to be deployed for decades. And yeah, the system might be used for triggering acoustic releases, and likewise modem functionality as well. I'd also just like to spend a second talking a little bit about the way that we describe how our systems perform compared to other vendors, because we all do it completely differently. So the USBL system is a USBL system. But when you look at a data sheet, our system is going to say it gives you a different value to another system out there. And I just want to make it clear that in this day and age, in reality, pretty much all the top-end USBL systems out there do a very, very good job. They all perform to roughly the same sort of performance. You might get a slightly better range out of one, and one might be slightly better tuned for something else. But realistically, they all do a really good job of tracking beacons. It's not like 10 years ago where we weren't all using digital signals. Everything's digital these days, really robust, really good. But on your data sheet, you're going to get lots of funny numbers, and they're all going to be completely different. So at Sonardyne, we do slant range. So that's just a percentage of the overall range is your error. Some companies do angular accuracy. Again, it's just the angle. That's all it is. And some report different statistics as well. So we do one DRMS, which is 63% of all your positions going to fall within a certain area. Some do CEP 50. So just bear this in mind is all I'm saying. We get a lot of questions about how well is the system going to perform compared to something else. And we always say, we give you a data sheet, but the best thing to do is get a system out there, try it on the vessel. Because yeah, a data sheet is only as good as the system's only as good as the final calibration, Okay. Right. A little bit of system optimization. So apart from the deployment system, the next biggest problem we face is noise. Noise is the one thing that trips these systems up more than anything else. And we've got lots of tools. We've got lots of things that can help us work out what's going on underwater. So we'll show you a video, and in the video, we're going to go and do a quick noise plot, what we call a noise plot. And we're just measuring what's going on around the vessel. And this example, we've got, yeah, this is fantastic. If you had a noise plot like that on your vessel, I would pretty much guarantee the USBL system is going to work very, very well. However, if you look in the top right corner, we've got peaks, there's spikes all over the place. And just so you're aware, the frequency is along the bottom, and then the level, the dB level is on the y-axis. And we can do these noise plots, and we can look at them, and we can get an idea of what's going on. We might see an outlier spike, but we might want to do it over time as well. We might want to plot that over time. So we can do a waterfall plot. But I've got some examples here. Right. So this one here. Any idea what this one might be? A spike at 55 kilohertz, pinging at about 1 hertz. So this one was an ADCP, vessel-mounted ADCP. And there's a few things here to look at. So this is actually outside of the frequency we're going to be operating the USBL system, but it can still affect it. It can still impact it. So what we'd want to do in this case is we'd want to pick a frequency for our USBL to operate as far away from that 55 kilohertz as possible. And we can also see on this, there's 3 lines. We've got a red line on that top graph. We've got a red line, which is the peak, the maximum we've recorded. We've got an average, and we've got a current. And what we can do is we can see that that's occurring every second, and it would impact the system. Another example, look at that one, horrendous. On first instance, you think it's really bad, but that is a one-off occurrence across the full spectrum. This is 0 to 60 kilohertz. And that's likely an engine or a motor or something starting up, but it only happened like once. And actually, when we look at the rest of the vessel profile, the noise profile, I would say that's average for an offshore support vessel. It's probably quite high for a research vessel, but average for an offshore support vessel, a newer one. But again, we'd probably want to pick something either, in the higher frequency band for this. But there's no noise spikes, which is good. Right, there we go. Some classic photos. So why isn't my USBL system working? Or have you checked it? Yeah, I mean, it goes without saying that maintenance is key with these systems. It really is. And people ask us, how often should I check? How often should I inspect my transceiver? And it really depends on where you're working in the world. For example, in the Middle East, extremely warm water, very shallow. These systems can end up looking like that one at the end within a few days quite easily. And other systems, they can go months without having to be cleaned. And a few things to sort of make you guys aware of. So the hard marine growth, as you can see there, sort of the top middle picture of the guys with the orange overalls on. Hard marine growth isn't actually that bad. There's a lot of space around it, so it's actually not too bad, and the systems can work. The problem you've got there is the hard marine growth starts to bite into the polymer that we use, so it starts to break down the plastic. So you might not see any acoustic issues with the system, but you're definitely going to start to see a hardware failure at some point. Soft marine growth, on the other hand, this will throw all sorts of spanners into the works. It basically traps air. It's trapping air around the transceiver, and once you've got air around the transceiver, we're up against it at that point. Trying to transmit through air is pretty much impossible. And this is where you'd start to see the acoustics start to fail quite quickly. Something that we do, or we used to do as offshore field engineers, when we installed the system, is we'd actually put a little bit of washing up liquid, a little bit of detergent over the face of the transceiver. And that actually helps. It's a very, very quick, simple fix, but that stops marine growth binding onto it immediately. So it's a very cheap, low cost solution. And we sort of recommend that you go and check it, once every couple of weeks if possible. And what that means is you have to have the method within your deployment system. You have to be able to go and inspect it. So having a dedicated deployment system with a sea chest that you can open, so you close a gate valve, drain the sea chest, open it, get in there, inspect it, is really, really important. It's no good deploying this on an over-the-side pole that you can't get to without having to get the crane involved and lift it back onto the deck. So it's just something else to consider. I'd also highly recommend training. I think as a support engineer, which is what I used to do previous to this for Sonardyne, when we're dealing with trying to get customers up and running remotely, a lot of the time it came down to them not fully understanding what the system's doing or what they're looking at. And they'd send us through a calibration report and say, "Oh, just make this better for us because we can't go on higher until we get a specific number." We say, "But you haven't done the calibration properly. We just can't do that." So definitely training, getting the guys, getting everyone up to speed as to how these systems work is really, really important. And I'm not saying that you come to Sonardyne in the UK, you do your training, like our guys will come to you. We see the research fleet as extremely important. We've got offices based in the US in Houston, but we will come to you guys and we can show you on your systems how to get it up and running. So please just reach out to us. Okay, so that's some of the sort of the high level ways to get the systems optimized, but there's definitely some fine tuning we can do. Okay, so again, we've got another video here. It's just going to run through how we start looking at some of the diagnostic tools we've got in the system. So when you're tracking with our system, tracking a beacon, we've got a traffic light system basically. Green is good, amber, I received a signal, but it's not very good, and red, something's not right. And what we can do is we can actually start looking at when we receive that signal, what might be causing the problem. So is it noise, for example? Is there just too much noise in the environment? We've done our noise plot and it actually looks okay. So we don't think it's noise. So could it be something else? Well, we can look at maybe the cross correlation. And what that means is that's us looking at the signal we've received compared to a perfect signal that we store in the system. And we map the two across each other. And that'll tell us if we're maybe getting some interference. And you can just simply hover the mouse over the icon and it'll tell you what the value is. And you've got a lookup table, you can go to your lookup table and say, right, yeah, this is out of spec. There's something going on. I'd say 9 times out of 10, you just got to increase the power of your beacon or reduce the gain of your transceiver. So there's too much noise in the system somewhere, whether that's external, whether it's internal. You might also find that you're trying to interrogate something too quickly as well. So you might want to turn down the update rate. Now, that's all well and good at the surface, but what if there's stuff going on subsea? Well, we can do exactly the same underwater as well. So we can get the surface system fine-tuned really, really well. But if you've got a beacon and it's on a really noisy ROV, or what we tend to find is if an ROV, particularly ones with hydraulic thrusters, if one of those starts to go down, it gets very, very noisy and it tends to sit in the frequency that we're trying to operate in. Or you might have other sensors on the ROV that are interfering with it as well. And we can do exactly the same. We can basically do it's like a noise plot, but underwater. And we can do that completely remotely. You don't need any cables going to the beacon. You can just say, take a background noise reading, send me back the data. So that's really, really useful if you want to check for any issues on the subsea vehicle that you're on. Or it also might be the environment that it's deployed in. We've got a system installed on the Chiku, which is a deep sea drilling vessel. So she's operated by Jamstec in Japan, and she does deep sea drilling through faults to try and look and investigate earthquakes and tsunamis. So she's a scientific drilling vessel. She deploys all sorts of equipment on the seabed, and sort of 6,000 to 7,000 meters water depth. We found that she was putting systems on the seabed, and some of these systems for measuring movement, tectonic plate movement, was interfering with the USBL system. And we were able to diagnose that because they were able to switch them on and off whilst we were measuring in real time what was happening subsea. So this is a really, really useful tool. It also, as I mentioned earlier, it's quite a good way of detecting if something's about to fail before it does fail. That's particularly with ROVs and AUVs. it normally means a reterm's involved as well. So the RV guys don't like it, but high elevation tracking. What do you mean by that? So we mean basically you're trying to position something that is relatively shallow, let's say in the water column, but from quite a long way away. So we call that high elevation. And there's lots of issues around this. You can choose a different frequency if you want to. You can go for a higher frequency signal, and that might help a little bit. But in reality, you're fighting physics at this point because you've got lots of stratification in the water column. So you've got lots of refraction happening through the water column. And yes, you can put a profile in. You can take a sound velocity profile and add it to the system. But you might find you're just not getting the signal through because it's bouncing around. You get multipath system bouncing from the surface through these stratified layers. And it's just a very difficult environment to track in. Even if you've got a completely omnidirectional receiver unit on the vessel, you're still fighting noise. You're still trying to get through the vessel's thrusters a lot of the time. It's a very, very challenging environment. But there's things we can do. A really basic one, we just use the depth sensor in the beacon. Just set it up so we're using the depth sensor in the beacon. And that way, you don't have to worry about multipath, you don't have to worry about refraction. We are simply just taking the beacon's depth sensor and transmitting it back via the modem link back to the surface. And then all we're doing is we're just saying which direction it's coming from. At that point, that's all we're measuring. And we can do that in a very, very neat way now as well. So with the advances of AUVs, being able to position and communicate with the vehicle without any sort of tether at all, we've developed a very efficient way of doing that. In that, when we send a signal out, we say, previously what we'd do is we'd send a signal out and say, where are you? You'd get a reply, and you'd say, and how deep are you? And you'd get a reply. Now what we do is we just say, how deep are you? We get that reply, and we also use that for the positioning as well. So it's a single transmission, and you're getting all that data back. So it speeds things up significantly, and it also improves on the battery life as well. But yeah, speeding things up. But yeah, I'd say there's a lot of issues caused around trying to operate near the surface, and a lot of it is noise induced. But we can start looking in and diagnosing what those issues might be and where the noise sources might be. But importantly, we've got lots of tools around us, and they can change the depth sensors. We can have really accurate depth sensors as well. So we can get centimeter accuracy depth pretty much in any water depth. Get that back to the surface. Okay. Could I get a quick show of hands if anyone's familiar with our data analysis tool, the DAT tool, which is sort of something that we do offer for analyzing the USBL data? Right? Okay, great. So it's a tool that Sonardyne offer. I believe a few of the research institutes have been given a copy of this. So let me know, because if they've got it for free, everyone else can have it for free. And what it will do is allows you to basically look at all your data offline. So you can analyze all of your data, and it's really, really powerful. It's not the easiest bit of software to use, I'll be completely honest with you, but once you get your head around how it works, it's really straightforward. And yeah, basically, if you were to have an issue offshore, we'd ask you to send it to Sonardyne, and we say, right, send us this particular file. And it might be a few hundred megabytes. If you've got lots and lots of data, there might be 10 meg. And you send it to us, and we put it into this tool. And it basically gives us a breakdown of everything that's been going on in the last sort of hour, 2 hours, 3 hours of your system's operation. And we can go in and we start to look at exactly what's going on. We can plot up some graphs. But the one graph that I would say is the most important. These are all the graphs you can plot up, but the one is the grid position. I think that's the one that you can start to look at straight away and determine if something's not quite right. I've got a bit of an example here. So when we're looking at trying to fine tune these systems and get them working, you might have already done a calibration on your system, but you want to prove that it's working correctly. So when we used to commission these systems offshore, we would do two tests. We'd do a spin test, spin the vessel over the top of the beacon, and a sail away test, sailing a distance away from the beacon. And that basically is testing two things. It's your lever arms and it's your heading offsets. So in this example here, we're getting the vessel to do a spin test over the top of the beacon. Something wasn't quite right. We look at the file and we can see this. So the internal ring here is the beacon position. The external ring is the vessel's position. So that's basically GPS position. And we've got a classic shape here. Donuts. The donut. Instantly, we're saying, right, we've got a lever arm problem. And because this tool is offline, we can actually start doing some pretty good diagnostics in it straight away. We can see we've got about 10-meter bust there. Can then go back into the system. We can start looking at where that lever arm error might be. So we know we've got 10 meters of error. Is it between the GPS antenna and our vessel reference point? Is it the transceiver to the vessel reference point? It's more likely to be a bit of both, if I'm being honest with you. But it allows us to factor in where that error might be. And it also quantifies it. So you're not shooting in the dark there. So the next test, the sail away test. In this test, the vessel will deploy a beacon and then just sail off, ideally with a fixed heading away from that beacon in a straight line or as straight as possible. And what we're looking at here is any deviation from that initial starting point of the beacon to when the vessel moves away. And it can be quite hard to look at it when you're doing it live online. So again, we're logging the data, we get it sent through to us, and we can start to look at what's actually going on. And you end up with this L shape. Now, this L shape, again, the beacon position or the measured beacon position is on the bottom there. It's that little short line on the bottom. The vessel position is the straight line, the vertical straight line. And what we're seeing here is that the perceived position of the beacon is moved. I mean, the beacon hasn't moved in reality. It's been on the seabed. It's fixed, hasn't moved at all. But the USBL system is reporting that it's moved. So we know that something's not quite right there. We can start to zoom in and do, again, some analysis on it. So we can see we've had a deviation of 33 meters from truth over a distance of 500 meters. That basically gives us an angle. And we know then we've got a 3.7 degree heading offset error within the system somewhere. So you can go in and you can start to look at where that error might be. Is it within the calibration of the USBL system, which is quite likely? And what I would suggest with these two examples here, so we've got a lever arm offset and we've got a heading offset. What I would suggest is just go and do another calibration at this point, because that will just take all of these errors, it will measure them and it will factor them into the final solution of the system. But this tool, it's available to all of you. If you want it, let us know. What I'd suggest is we do a little bit of work on the best way to use this tool, so we can spend a bit of time with you. We can do that remotely, get the guys to come down and visit you. Yeah, it's really, really powerful. It's what we use to diagnose any issues offshore ourselves when we're in the office. And yeah, it needs a little bit of getting used to, but it is really, really powerful. And with that, it's going to come to the conclusion, really. Yeah, so pick the right system for the job. Number one, install it correctly. Number two, train and maintain. Without a doubt, to keep these systems operational and working correctly, it's the most important factor. And we've got lots of tools available within the system to fine tune it. Loads of tools available, and they don't have to be online. We can work offline to look at what's going on. And yeah, with that, I'll conclude. Thank you, and please, lots of questions if you have any. Good. Yeah. Okay.
Can you give any comments on beacon frequency selection?
I can.
Doesn't look like
No questions. Okay. Yeah. Beacon frequency. So, so we sort of have two categories. You have low frequency beacons, and these are the specialist ones that are designed for transmitting very long range between, say, 12 and 19 kilohertz. I would say they're kind of specialist, and you need a different hardware set on the vessel to be able to talk to those. The US research fleet all have medium frequency systems. And by medium frequency, we mean 19 to 32 kilohertz. And that is kind of industry standard. But that's a big frequency range. So the higher the frequency, the better the resolution on those signals, the more wobbles you've got per second, basically. So if you're doing high elevation tracking, or if you need extreme precision, choose a higher frequency signal. However, you might find that you get a lot more interference with that signal. There's a lot more to go wrong. If you want to transmit a signal slightly further and resolution isn't as important, you go for a slightly lower frequency choice. Now that's what the manuals say, and that's great in practice, but there's a lot going on within that. So we have and I've been given the green light to provide you with our training material as well, which has got some good information about this in. We have what we call our interrogation signals, and that's what the transceiver on the vessel is saying, right, talk to me, number 2501, or whatever it might be. And then number 2501 replies on a different frequency channel. Those interrogation signals are fixed, and they're fixed to be a combination of robust and highly accurate. So they sit at a fixed sort of frequency in the middle of our frequency table. But what you can then do is decide where you want the reply coming back from, whereabouts in the frequency table you want it to come back from. The other thing to factor in here is vessel noise. So you might find that even if you're at the lower end of our frequency band, you're still getting quite a lot of vessel-borne noise, and that might interfere with the system as well. So the noise plot is number one. That's where to start. The frequency lookup table as well. I've got a really simple one. I found a really simple one that makes it very clear, because we published quite a few over the years, and they're all gobbledygook. They don't make any sense at all, even to me. So we've got a really simplified one that tells you where these interrogation frequencies are, where the reply frequencies are, which I think will help, hopefully. Yeah. Oh, yeah, go for it.
Just check really.
Yes.
So probably a simple one. When you use your Dawn dish soap or whatever detergent you're putting on it, how long do you see that typically?
Yeah, it's not long at all. What it tends to be good for is if it's a brand new system and you want to go and try and get a really good calibration on it. So it's just like another step that allows you to get the very best out of the system. It washes off very, very quickly. It really does. Yeah. But it's just a very simple, cheap solution to, I mean, if you went down and did it every other day, you'd probably have no marine growth buildup at all. But no one's going to do that. Yeah.
Okay, how about like grease with pepper, or something like that? Have you heard of that?
I've never heard of that before. No.
Thinking.
Yeah, potentially. Yeah. So we've done a fair bit of work on coatings, so coatings for biofouling. And what I would say is they all have a detrimental effect on the performance of the system. But in reality, it's definitely better than letting marine growth build up. So if your maintenance procedures are really good, I don't really think you need anything, if I'm being completely honest with you. Just get down there, inspect it, and give it a good old clean. But if it's in a difficult environment to get into, that you've got to vent for 24 hours before you can get in, and it's a struggle to do it, then maybe some sort of coating it could be worthwhile, and it does affect it, but not significantly. Yeah. And so a lot of I'll give you an example. A lot of the drill ships, these things are massive. They and these are deployed in the bottom of the hull. They have to vent them for 24 hours before they're allowed to go into space. There's lots of lockout tagouts in place. It's a very complicated procedure just to get in there, let alone to drain the sea chest. To then you've then got a single point of failure on the hull. They don't like to touch the systems once they're up and running. So yeah, sometimes they've applied coatings, but please don't just go and apply anything. Please contact Sonardyne because we've got lots of testing to prove which ones do work. And particularly for you guys, they've got to be eco-friendly as well. So we've got all that information.
Okay, another one. You commented on using the pressure sensor, and my personal thoughts are you need to use some caution with that. And I don't know if you can comment a little bit more on that, but in particular, we've run into trouble because, for instance, the nano beacons are rated to a greater depth for the housing than the pressure sensor is. And it doesn't damage the pressure sensor, but once you get below its limit, it keeps reading you the same depth, and it really messes up your position.
I would say that's faux pas on our part, because if it can go to a certain depth, it should be able to report that depth accurately. So the nano beacons, if anyone's not familiar, they're about this sort of size, really, really small. In fact, a little bit smaller than that. Designed very much for quick ease of use. Some of them don't even have any connectors on them. They charge up wireless charging, NFC for configuration, really designed to just be strapped on something quite small and off you go. But if you go to some of our slightly larger beacons, then you can have proper depth sensors fitted in them. Yeah, some of the units that we use for high accuracy subsea positioning, you've got digiquartz sensors and things like that in them.
Have you seen anybody else? So we can flush our ducts. I think we're doing it sometimes. We can either put fresh water in there or air and just empty it, and then you can reseal it, and the pressure should stay enough to keep the water out of it. It seems like a good idea, particularly if you're not doing any USBL for a few months. Do other vessels do that? Do you have a recommendation on it?
Yeah. So particularly polar class vessels, they'll tend to flush it, dry it out. The one thing to be careful of, though, is once you have flushed it, if you do dry it out, is that when you come to flood it again, you need to make sure you get all the air out, because you might end up with an air pocket in there. So it's just something for the techs to be aware of, that it's very good practice. We recommend it. In fact, we do recommend it. Yeah, but there's just, when you come back to operation again, you've got to make sure you flush all that air out, and that's normally straightforward. There's just a couple of valves that you can open and close.
Weapon doors are all on bolts.
Yeah. Yeah, excellent. There are some instances where, again, we find in the Middle East where they leave the sea chests flooded, and they normally leave the system switched on as well, and they can start to heat up really, really quickly. So maybe not something you guys would experience, but it's something to think about. These systems, if they're operating, they're pulling about sort of 30 watts sometimes, so they can really start to warm up. And if it's in an enclosed area that's wet, it can get quite warm.
Have you seen failures from leaving the system on for long, while in the sea chest?
Not in the sea chest. No, sea chests tend to be pretty good. It tends to be on systems that are deployed over the side of vessels, and they're just left out in direct sunlight. So sometimes we'll find that they'll fabricate a pole, and when they recover it, the transceiver array is facing directly into the sun in some instances, and especially in warmer climates, it can damage them. Yeah, without a doubt. We have tried to do some engineering around it to prevent there being any issues around that by putting pressure relief valves into the housings, but we're kind of fighting a bit of a losing battle at that point. So yeah. Yeah. I will. Yeah, we've got lots of training material behind all of this. This presentation is available to anyone that wants it as well. There's some videos in there, so it's quite large. But the training material that's sort of behind all of this is probably where I think you'll find the most use. So yeah, I would say please contact me for that training material and I can distribute it. I've had, like I said, I've had the green light from our training team to be able to do that for you guys. Okay, no problem. Thank you. Oh, sorry. One more thing. There are some engineer notebooks outside. They're purple. They're the perfect size to put in your coveralls. They're really, really good. Please grab one. But also, we're going to be back here again beginning of February, and we're doing a bit of a combined demonstration. So Sonardyne and Voice do laser photogrammetry systems. Actually, incredible bits of kit. But if you're interested, there'll also be a lot of USBL in there as well. So that's beginning of February. These are some cards outside, QR codes on them, contact details. If this type of stuff is really interested, if you're interested in it, please, I'd recommend trying to attend this as well. Thank you.
Thank you very much. So we are going to come back here at 9:45, right after a break. And talk about vessel acoustics.
I know. I just want to see. Yes. Right now, I'm great. You gave me. You have. Oh, let's see. Yeah, it's. We made things up. But now going almost that far. So nice to meet you. Yeah, it's really probably hurt. Oh yeah. It wasn't. I just want to say something. Yeah. At least. You're a genius. Yeah. Yeah.
Uh,
Yeah, so go ahead and just type it in there. I told him to stand by.
oh yeah, cool. Sorry.
Oh, that's okay. It's Melissa Small who's asking. It's easier, if you do it.
Yeah, yeah, no worries.
I'll probably mess it up. The Zooms just stays open,
Oh, right, yeah.
so it's no problem. Add additional information later. If you could also
Perfect.
connect via your laptop too, if you want to. Session.
Oh, right. Oh, okay. Yeah, I did
So,
see that. Yeah.
yeah.
Yeah, excellent. Okay. Yeah, sorry about that plug at the end, guys.
Please.
It's back here again, so it seems worthwhile mentioning.
It's okay. It's okay.
So. It's all.
Okay, it's being recorded. Does this bother you here?
No,
We could.
it doesn't probably.
It doesn't have to be here. Oh, wait. Okay, well, at least this way it's a little smaller. Okay. All righty. Is it that time? Should we go ahead and get started?
No, we can find it.
Yeah.
Well, that's okay. I didn't know if you just wanted me to start, so.
I'll let you just see. All right.
Okay.
Okay. So, hello, we are going to go ahead and continue. And Tim Gates is going to do a presentation. Thank you so much for your attention.
Well, good morning. I'm going to talk today about really noise on ships. I'd like to give you guys a little bit of a background on me. I've been around a long time. I graduated in 1980, and in 1981, I rode my first nuclear submarine. And I spent about 800 days underwater over the next like 10 years testing nuclear submarines, making them quiet. So that's where I started. I started with the military. It was a little different back then because if you were a loud submarine, it could be a life or death situation. Now, you don't have life or death situations, except maybe some chief scientists make you think that way. But, it's still the same principles. So in the late 80s and early 90s, I shifted to some special projects with surface ships. I actually worked on the first multibeam in the world, which was a classified military sonar that was installed on one ship. It was called the SAS. Some of you may have heard about it. And then that migrated into other multibeam systems. That you had the Krupp Atlas Hydrosweep, you had the C-beam, and then you had the Kongsberg, which became available in the early 90s. And so I spent a lot of time working with all these systems as they were developed. In 1994, the Naval Oceanographic Office got their first multi-beam, and then they really, really put it on 6 ships in a row. they had a lot of noise problems with those ships, and they engaged my services working with the Naval Surface Warfare Center to figure out why their systems weren't working. And we did a lot of work on those ships to get them up to speed, which I will discuss in my talk. And then that brings us to the UNOLS community. In about 15 years ago, the UNOLS fleet that had Kongsberg multi-beams all were complaining that the systems weren't working. So the National Science Foundation, Jim Hollick, had to come to the principal meeting, and he invited representatives from all the UNOLS ships that had sonars to come, and he invited the Navy to come. And almost without exception, the UNOLS program blamed the sonars for not working right. And so Jim Hollick asked the Navy, do you have the same sonar? Well, the answer was yes, we have the same sonars. And are your sonars working? They work perfectly fine. We're getting everything that the vendor says we're going to get. So he wanted to know what the difference was. And my customer at the Naval Oceanographic Office said, we spend money to make our ships quiet. That's why our systems work. If you don't spend the money, if you don't take the effort to make your ship quiet, then your sonar is not going to work very well and you're wasting your money. So that meeting was basically the beginning of the MAC community, the multi-beam advisory community. It was discussed. I was part of the original grant with Paul and Vicky to put the grant in place. And in the beginning, we actually tried to go out and test every UNOL ship, 2 UNOL ships a year, just to try to get all the UNOLS fleet, into a more quiet mode. And I think that was pretty successful. And hopefully there was a lot of education in the community about what they need to do. And so I'm just going to discuss some of those things. And then I have a lot of examples of noise issues on ships. And I'd like to make this more of a workshop kind of thing. So interrupt me if you'd like. If you have a question, don't wait to the end, because you might forget about what you wanted to ask it before this thing gets to the end. But with that, I'm going to talk about why acoustic noise is important. Obviously, the louder your ship is, the worse your sonar is going to work. It degrades sonar performance. There's another part of that, which I'm just going to touch on, is a very noisy ship radiates noise into the ocean, and that has a negative impact on marine life. And while that may not make an impact on your sonars, we are trying to green the fleet. We're trying to make these ships less, of a negative impact on marine life. So silencing your ship has a positive impact on the environment as well. If you have a degraded sonar performance, your quality of sonar data goes down, and what that does is it makes you spend more time on station to get your data. And your time is precious. A lot of your missions, your chief scientists wait years and years to get out, and if they have to spend extra time or don't get their data, it's very very unfortunate for them. So these are the types of ship related noise that I see over my career. Machinery noise, and machinery noise is any kind of reciprocating, rotating machinery that puts frequency components into the data, into the water. It's not typically a big problem with sonars because the machinery noise is typically less than 2 kilohertz, and the sonars are usually much higher, but we have seen some cases which I will talk about. Electronic noise, which is EMI, crosstalk in cables, things like that. Propeller cavitation off the hub and the tip of the propellers as you go through the water at various speeds. We get hydrodynamic flow noise, which is just the noise that the water makes when it flows over the hull. The smoother the hull, the lower the noise is. A lot of organizations are going to a gondola now, which sticks down below the hull, and that is a definitely impact on your hydrodynamic situation. The flush mount is better, but you get bubble performance with the gondola, so you need to design it so that it's nice and faired in with respect to the flow lines going over the ship. Appendix cavitation, that's things that stick out into the water flow. If the water pressure drops from one side to the other low enough, it can make the water rupture into cavitation. That can be a quite noisy phenomenon. Transients are things like even as simple as slamming doors or pumps that come on for a few seconds and turn back off again. And then bubble sweep down, which is when bubbles get entrained in the flow under the ship and get below the sonars. And when that happens, that's the kiss of death. Your sonar won't work anymore. The acoustic energy does not propagate through air. So, you really want to try to avoid bubble sweep down. This is the only formula I'm going to show. It's the only one relevant for what we are talking about today. It's the active sonar equation. And simplified, it's signal excess equals your source level minus 2 times your transmission loss minus the noise of the ship itself. So your signal excess is typically fixed. The sonars that you guys have on your ships typically need about a 10 dB signal to noise ratio in order to process it and give you proper results. The source level is the noise that the ping makes when it comes out of the sonar. That is controlled by physics. You can only ping so loud. If you ping louder than the allowable limit, the ping will actually cavitate at the transducer face, and it'll not get into the water. So physics controls how loud the ping can be. Your transmission loss is completely driven by the depth of the water you're in and the frequency that you are transmitting at 12 kilohertz. You typically lose 1 dB per kilometer of absorption, and the spherical spreading from the transducer to the bottom is 20 log the range. And then you get some loss on the bottom based on the reflection, and then you have to double that because it goes down and back. And when you're looking at these multi-beams that are going 60 or 70 degrees on either side, they have to go very, very long. So you get a lot of attenuation. And all of those are controlled. The only thing you can control is the LN, is the noise of the ship. If you look at this formula, everything's weighted the same. 1 dB of noise on the ship equals 1 dB of reduced signal. So we have to put our attention to controlling the noise of the ship because that's the only thing you really can make a difference. So just remember that my talk is going to be telling you over and over again of how important the noise of the ship is. So if you have a new ship, you're lucky. You need to design it, and you need to design it for quiet operations. There's a lot of work that goes into that. Most of the community, deals with naval architects that understand this, and all of the new ships have been pretty well designed for acoustic strategy. They have a lot of silencing features built in. but once you design it, you have to build it, and building it is a challenge because the shipyards sometimes don't understand what they're doing and why they need to build a quiet ship. These are not cargo ships. These are ships that have acoustic missions. So you need to pay attention to the construction. And then once you have your ship built, you need to test it and maintain it. Usually, when you're building it, like most of the Unol ships were built by the Navy. Actually, the Navy has facilities that they build it and maintain and test it at delivery to make sure it's quiet. But it's up to this community to maintain it over its life. I want to just talk real briefly about radiated noise, because there's been some issues back and forth. And I'm currently working on the NOAA ships, the NOAA Class A, Class B, and Class C, and some of the NOAA ships have fishery missions, so they have to meet something called ICES 209. And if you don't meet the radiated noise of ICES 209, your data is not considered valid for fishery stock assessments. But if you don't have a fishery missions, why do you care about radiated noise? As I mentioned before, we want to make the ships quiet. I'll get to the sonar in a second. So if you decide you have a radiated noise specification, which we do, and the Neil Armstrong and Sally Ride both have radiated noise goals, and that was just for environmental reasons. So they didn't have fishery surveys, but they just wanted to be quiet. So we came up with what we call it ICES Light. The top curve is the NOAA. I mean, not the NOAA. The top curve is the Armstrong and Sally Ride goal, and that's also for NOAA Class A and B. If you're going to do fisheries, it's much more stringent. The red dots, that's a fisheries ship. If you don't meet the fishery ship goal of the red dots, then your data is not considered as valid. I don't think you guys are really going to get into fishery missions, but I just want you to be mindful that when you're thinking about new ships, you do want to maintain a good environmental posture. Now, sonar self noise, that's really the meat of the matter here. You have to know what your ship is going to do. Is your ship going to be a deep water ship? Is it going to be a hydrographic bathymetric ship? Is it going to look at currents, or what is it going to look at? Because once you have your profile, then you have to determine what your sonar suite is going to be. And every sonar has a different operating frequency. So once you get your sonars lined up, you look at the operating frequencies, then you have to focus your design efforts and your funding on quieting the vessel at those frequencies. If you only are working at 12 kilohertz, you don't really care what happens at 5 kilohertz or 15 kilohertz. So spend your money to make sure it's quiet at the operational frequency of the sonars. Using that equation I talked about, you come up with what's the maximum self noise levels for each operating sonar can be. And you probably haven't seen it, but for your ships, there's a construction guidelines that has that table in it. We generated for all of these sonars, and I noticed it's been shared. I saw that it's been cut into the RCRV ship, so it's kind of perpetuating itself, and it's the table of the levels for each frequency of the sonars that you have is well documented, and if you meet those levels, then you should have a quiet ship. You need to spend time on your propeller design. You need to address bubble sweep down, and you need to make sure your sonars are properly installed in terms of orientation, faired in properly, and located properly. We just had a NOAA Class B. NOAA didn't use the Navy to design the ship. They sent it out to another organization to come up with a ship design. And they initially had the sonars located in the back of the ship underneath the engine room. And well, that's not a very good idea. So we've changed that and are working forward to groom that design. We don't like to see propeller cavitation at any mission speeds. A good ship should be able to not cavitate up through about 11 knots. So that should not be an impossible challenge. You need to isolate all your machinery and piping within the way of the sonar. We have fairness criteria, so how smooth the hole needs to be within 6 meters of the sonar transducers. And sometimes you have to pick optimized quiet machinery, and that's more expensive. If you go off the shelf and you buy a regular pump, you might get a pump that works, but it won't be a pump that's quiet. So you need to pay attention to all of that. When you're building new ships, you need to do modeling and predictions, and so that you're not surprised with what you get. We do very detailed construction processes. We make sure all the requirements are met, and we have somebody on site when these ships are being built to make sure the shipyard is doing it correctly. Now, I know when you are upgrading your ships, you have on-site representation from the organizations, and they just need to stay on top of the shipyards to make sure that they don't violate acoustic boundaries by changing things that they shouldn't. Now, once you have a ship, the very first thing you should do is do an acoustic baseline. A brand new ship is most likely going to be the quietest it's ever been in its life. You should take an acoustic measurement, at delivery, and use that as the ground truth for the life of the ship to compare back to make sure you're maintaining what you have. And that baseline will verify all your silencing treatments. And when you change things in the future, you can use that to make sure that you didn't degrade the capability of the ship. Because if you don't do anything, the ship's not going to stay quiet. Over time, it's just going to slowly get louder and louder. And so you have to put effort in to keep your ship quiet. Now, many of the UNOL ships now have acoustic monitoring systems. The Kilomoana, the Thompson, the Atlantis, they all have hydrophones that I left behind after I tested them, but they don't have an electronic capability. They can listen to the data. The new ships like the Armstrong and the Ride, they have electronics that they can actually listen and amplify and filter the data. And the RCRVs and the NOAA Class A and B are even getting a better system that's now available. And if you can afford it, I would recommend, if you have a ship, you should put something like that on so that your techs can actually do a quick acoustic assessment, and they can listen to the environment when they're taking data, because the first line of defense against any noise issue is just listening to the water. What do you hear out there? Do you hear pumps coming on and off? Do you hear transients? What are you hearing? And you also get to hear marine life as well. So that's the plus. So now I'm just going to get into some examples of noise issues that I've found over time on oceanographic research. The first example is from the Roger Revelle. And the bottom curve is the baseline, and the top curve is what happens when they flush the toilets. And this is a transient, but probably every 2 flushes, it kicks on the vacuum system, and the vacuum pump makes a lot of noise. It's funny because this transient happens a lot more after meals. And if they serve something like chili or something spicy, it happens quite a bit. So, and I actually am not making that up. You can actually almost predict things based on what the meal was. But if you look at the bottom line, which is frequency, the main system, which I'll talk about this system mostly, is the EM124. It operates at 12 kilohertz. So this at 12 kilohertz is increasing the noise about 14 or 15 dB. Every 6 dB is a doubling of the noise. So that's a significant impact on your sonar. Now they have quieter systems, and a lot of the ships have gone to quieter sewage and vacuum systems. But for a long time, the sewage system was always a problem. And another reason it was a problem is because for some reason they always put the sewage system next to the sonar void, and I don't know why, but you have to put it somewhere, and so they put it on the front half of the ship. So sewage was always a problem. The next example is Kilomoana scientific seawater pump, and the Kilomoana is a swath hull, so it's a twin hull. So the sonar was on the port side, and this pump was on the starboard side, all the way up forward. And it was a little itty bitty pump, just a tiny pump. But because it was a small pump, it had to work harder. And you can see at 12 kilohertz, that was increasing the noise about 6-7 dB, which was quite a bit. And nobody thought this would be a problem because it was on the other hole. It was far away, but actually that allowed it to be almost in the free field right next to the sonar because the energy would go through the water and go right into the sonar. So the solution to this was we put a bigger pump in that ran slower, and by ran slower, the noise levels came down, and we didn't have any problems after that. It was an impeller pump, and when you crawled down to inspect it, which was probably why no one ever inspected it because it was very hard to get to, you could just hear it screaming. So it was, just nobody thought that machinery on the other side of the ship would have an impact, but it did. Another Kilomoana, issue, and this is one of the rare cases where machinery has an impact. The Kilomoana has 4 diesel engines, 2 on the port side, 2 on the starboard side. The sonars are on the port side. And when you ran each diesel engine one at a time, these are the levels. And the 2 quiet ones were on the starboard side and not on the sonar side. And the 2 loud ones were on the sonar side. Now, unfortunately, the sonar compartment in the engine room shared a bulkhead. And so these diesel engines were quite louder, but that's a lot of dB. That's 10 dB at the emission frequency of the sonar. So there's 2 ways to solve this. One was when you're doing surveys where you needed a better signal to noise, and you operate on the starboard engines, you can deal with this operationally. But what we found is another problem is the engines were making more noise than they should, and we did a lot of investigations as to why. We actually put insulation down to try to decouple the airborne component. And during our testing with running the engines, they had an engine fire. And it turned out that they hadn't changed the filters on the engines and they were clogged and they caught on fire. When they put clean filters back in, the levels went back down to what they should be. So it was the ship was new, so it was the lack of understanding of the maintenance required to keep the ship capable. This is a impact of the engine noise on the Kilomoana. On the left is with the quiet engines, and on the right is the noisy engines on the sonar side, and you can see all the noise spikes in the data. So it's not insignificant. So just being aware of what's happening with your machinery lineup is very important sometimes. Now, here's an example from the Neil Armstrong, which is a relatively new ship. I guess in my world it's new, but it's still 10 years old. But they have, and a lot of ships now are going to variable frequency fans, and these fans are small and they're in the engine spaces, and they can run at different speeds. And this fan's about this big, and it's in the auxiliary machinery room. And when you turn it on, you see what happens with the red curves. Now, this would be a major impact if you had an EM 304 at 30 kilohertz, but the fan was not properly isolated, and you can change the frequency of operation to make the frequency components shift up and down. So we play with it, and it's not a problem. But it looks pretty ugly when you turn a small fan on, and that's the noise you get into your sonar environment. This is going way back to the Melville. The Melville, ignore that spike. That's a bad element in the sonar. But they have an active anti-roll tank. So it's a U shape that they actually pump water up and down on either side to combat the roll. I think every ship left in the fleet now has the passive roll system, which is up high, which has the flanges that it goes back and forth. But on the Melville, every time they turn the anti-roll tank on, it degraded the starboard side of the array by 10 dB. And this is actually sonar data, so that's a real impact on the system. So their choice was to make the scientists comfortable or give the scientists good data. And everybody wanted good data, but then nobody wanted to get seasick either. So it's kind of a choice you have to make. Now we're going to get into EMI, electrical noise interference. When the Healy was delivered 25 years ago, it had a C-beam on it. And we went out and took our first set of data, and this is what we got. So we were getting 30 to 40 dB of electrical interference in the data. And we spent a lot of time trying to figure out why. And we obviously had a really good idea. It was in the cabling. So what we did is we had the vendor give us a separate cable for the system, and we unplugged it from the sonar and unplugged it from the transceiver and ran it through the middle of the ship, in the middle of the compartments, away from everything, and the levels came back down to the red level. So we did a trace of the cable, and it turned out for a very short period they had shared the cable tray with the 4,000-volt propulsion cables. So it was just somebody at the shipyard wasn't paying attention, and they ran the cables in a very poor manner. And anytime you had any propulsion, it just bled right into the sonar, because the sonar, the levels of that data was in millivolts. So you're comparing millivolts to 4,000 volts. It's a huge amount of energy that just was bleeding into the data cables. So we ripped the cable out, rerouted it, and then the problem went away. This is the Nautilus. I think you might have been on board when we did this test, Sarah. Ultimately they had a bad UPS. You think your UPS is going to clean your data, but this thing was acting kind of funny. And we had this red curve that was, trying to figure out what's creating all this noise on the starboard side of the array. And the UPS died. So we convinced the ship in Kongsberg to let us operate with no protection. We plugged it without an UPS in, and all the noise went away. So if anybody watched the troubleshooting yesterday, this was a gift, because it blew itself up, and we recommended getting a much better UPS, which they ultimately did. But still, it would have been a hard time to find a problem when you think you're operating through a system that's designed to make it better. So this just be careful. Sometimes your UPSs do make noise. And now I want to talk about propellers a little bit. Propeller cavitation, as you go up in speed, is one of the loudest noises on the ship. And we found, and it's kind of amazing because we didn't discover this for years, on the TAGS class, the Navy's oceanographic ships. They have Z drives, azimuthine drives, that the direction that the drives point makes a difference in how much noise they make. And, they were designed to be pointing at 3 degrees out. So the front of the propeller, the toe is toe out. And that was designed to match the flow of the water and optimize its propeller noise. But we did a modification with the gondola on these ships. And when we put the gondola on the ships, we changed the directional stability of the vessel. So we had to add a skeg. So we added a 40-foot skeg. And when we added the skeg, it changed the inflow to the propeller. The flow was bouncing off the skeg and coming back to the propeller. So actually toe in was more efficient than toe out. So this plot is at the same speed, about 12 knots, just pointing the propellers in different directions. And we're talking just a few degrees. And we could decrease by 15 dB the propeller noise that was impacting the sonar by pointing the propellers correctly. So if you have ships that have Z drives or L drives, any azimuthine, stern drives, you need to make sure they're pointed properly, or you could create cavitation that would degrade your sonar. I have some more data on that. So this is actual sonar data right here, just changing the pointing angle. And that's a lot. It's almost 4 times less noise. And the impact in speed was less than 1/10 of a knot. And if there was no impact on fuel efficiency. So this was, it was shocking for us that we'd operated these ships for so long and hadn't figured this out. This is the John Hughes Clark plot. And it just shows the cavitation impacts. If you look at the outer edges of the swath as you go up in speed with the different pointing angle, the far right plot, you're losing all your outer beams because of propeller noise. Another problem that we found with azimuthing drives is they're not pointed straight to begin with. We had a lot of noise on this ship. This is the Tag 60, the Pathfinder, and it was from the propellers, and we couldn't figure out why. And in the testing, we realized that the ship kept turning in circles when we were trying to go straight. And we didn't believe it, but we put the ship propellers at 0 degrees and put a camera over the side. Well, this is what we got. The starboard propeller, when it's configured to 0 degrees in the bridge, was pointing 17 degrees off. So that right off the bat, is going to, make a lot of extra noise. So we started looking at all of the Navy ships, and they have 7 ships that are the same, and 4 of them had alignment issues. So we like to make sure that every time we go into a dry dock, that they put them at 0, and when you can actually walk up to them in the dry dock, make sure they really are pointing at 0, because once the ship's launched, it's really hard. And I don't know how many ships here have Z drives. I think a few of them do. There's a punch mark inside the ship that tells you that it's aligned to 0. Well, we found one ship that the punch mark was wrong. So just trust but verify. Make sure that your propellers are pointed correctly. This goes back to the Roger Revell days. This is the EM-120, a long time ago. We took our first set of data on the Revell, and this is the sonar data. So you get a data point at each of the elements in the sonar array from port to starboard. And this is at every speed from 0 to like 13, 14 knots. And you can see there's a problem in here. There's a repeating problem. Every 8 elements, there's a high noise spike. This is a Kongsberg problem. It has been fixed, but on the cable, every 8th channel, they use the strength conduit, which had a different capacitance. So every 8 channels had a higher noise level because of how it was wired. So they went back and provided different cables, and it made the problem go away. But just you would never expected that, because the cable would pin out correctly, but one cable had a higher capacitance. The Roger Revell, it had 2 kinds of cavitation that we had to deal with. You can see the circles, that's the cavitation off the tips of the propeller. That's normal. But if you look in the middle, I don't have a pointer. In the middle, there's a cavitation coming off the hub of the propeller, hub vortex cavitation. And that is not typical. And you put something called a dunce cap on and make it go away. It basically can unswirl that. But if you didn't do the testing, and we had divers film the ship when it was moving by us to make sure that this is what it was, so that it had some cavitation noise that was not expected, that we were able to eliminate with the modification. Now, the Marcus Langseth. That is a ship that has controllable pitch propellers. Controllable pitch propellers are very different than fixed pitch because they spin at the same speed all the time, and they change the orientation of the blades to determine how fast they want to go. So they have a design pitch, and the design pitch might be at 7, 8 knots. And then when they want to go slow, they flatten the blades. So the propeller is still spinning fast, but it's not pushing very hard. Well, when you do that, it gets louder, not quieter. So on the Langseth, actually, slowing down sometimes is not a good thing. And what you can do, go back up. What you can do is you can manually decrease the RPM if the chief engineer will let you, because they don't like to run their engines really slow. When you have an electric drive propeller, your engine is at the same speed, but the motor is variable. But with the Langseth, they didn't have that option. But we convinced the chief engineer to slow from 750 RPM down to 600 RPM. And at 600 RPM, you can see right now this is sonar data. So at about 60% pitch, which is about 8 knots, we were at 65 dB. but when we slowed it down, we got down to like 52 dB or 53 dB. So just understanding how your propulsion system works and the lineups, you might be able to operationally quiet your ship. Now we're going way back in time. This is the first Navy oceanographic ship in the modern era. This is the Pathfinder. This is in 1995, and they had the EM-121 Alpha, which was the predecessor of the new sonars we have. Well, back then, this was a new thing for Kongsberg, and they built a great sonar, but they didn't understand how to install the sonars back then. So this is the fairing that they slapped on the hull with the sonar. And you can see how ugly this is, how bad the lines were. And it had a lot of noise. It couldn't do its mission. And so this is the levels. The requirement for this sonar was it needed to be below 49 dB at 12 knots. And at this curve, it was 60 dB at 12 knots, which was a total failure. And they were going to be building 6 of these ships, and this is the first one. We needed to figure out why. Well, when we looked at the fairing, we had a good idea of what that reason was. So we just smoothed out the fairing. It's the exact same sonar, but we just changed it. It took a lot of shipyard work because there's a lot of compound curves, but we put a new fairing on it, and this is what we got. So we got right down to 49 dB. So we dropped it over 10 dB just by smoothing the installation of the sonar itself. As Duncan talked about, this is bad. His problem is different than my problem because his is just the ship's not really moving. You know, it's in dynamic positioning. But when you have fouling like this or like this, and it's moving, this dramatically increases the flow noise over the sonar. And this picture here, that is the sonar acoustic window. So when you have barnacles, it just tremendously increases the noise. This is the ship here that the pictures I just showed you before and after hull cleaning. And 600 RPMs at 60, that's 12 knots on this ship. And it went from 61 down to 45 dB just by getting rid of the fouling on the face of the transducer. And to give you an idea of what that does to your swath coverage, this figure shows that 8, 9, 10, 11, 12 knots with and without the cleaning. So you're getting, let's say, 12 knots. You're getting 12 and a half kilometers of swath when it's fouled, or 20,000 kilometers when it's not. That's real money. That's a lot of ship operation time. So grooming your ships before you go on missions is a good idea. Bilge keel cavitation. It took me 3 years to solve this problem. Some of your ships have this problem, but anybody who's ridden the Thompson or the Revell or the Atlantis before you put the fix on would have realized when you're going above about 8 knots and you had a roll of maybe just 4 or 5 degrees, there was a loud groaning noise. It was tremendous. And especially when I was out on the Thompson just 5 years ago, it was down in the berthing. It was so loud you couldn't sleep. It sounded just like, every wave cycle, every roll, you would just get a huge noise that would be maybe 30 dB above the background. And what it turned out to be, and this is with divers filming a bilge keel as we're going by at 11 and a half knots, when the leading edge of the bilge keel was coming up, it would cause a pressure drop below it, and that would cause the water to rupture into cavitation. And that it was consistent. It caused habitability issues and it caused some sonar issues. So we just modified the leading edge of the bilge keel, so you can see that the forward 4 feet of this is thickened and smooth. And we did this on all the tags Navy ships, and we've done it for the Thompson, the Atlantis, and the Revell now, and the problem's pretty much gone. And here's another picture, which is not supposed to be a bilge keel because I messed up on my presentation. The next picture was supposed to be a picture of the Atlantis gondola. The Atlantis midlife added a gondola, and it was designed by naval architects, and it was smooth and everything was fine. And then when they installed it, somebody looked at it in the dry dock and says, this thing is going to catch logs and stuff. So we're going to add a couple bars on the front of it to protect it so it would push things off to the side. Well, those bars cavitated and caused a degradation of about 5 dB at 11 and 12 knots. So they since cut them off and everything's fine now. When the Armstrong was delivered, we went out to sea the very first day, and it has the full-blown acoustic monitoring system, so you can listen to the noise. And every little roll we had, we heard a big thunk in the data, and it was with and without that transient noise. This is what the data showed us. And so at 12 kilohertz, we were getting a 10 dB transient. It turned out in the sewage tank that when the effluent in the tank would slosh from one side to the other, the float in there would come up and come back down and slam the metal. So it took a unfortunate shipyard worker to go into the tank and replace it. And once they put the right switch in there, the problem went away. But it's just these little things, you don't really know. Another Nautilus problem. It had a sound velocity pump, and the pump was cavitating, and that was the red curve, and that was increasing the sonar data by about 10 dB. So we put a new pump in, and it didn't cavitate anymore, and the levels came right back down again. I can't leave NOAA out. On the Alakai, which is a converted Tiego ship, the ship was designed to hunt for foreign submarines. It had the absolute quietest machinery plant that you could build when it was delivered. The ship was given to NOAA, and it's resident in Hawaii. And we went out, and they had some noise problems. And it turned out that the chief engineer wanted more space. So he welded brackets above and below the sound isolation mounts on one of his machines to store air bottles. So he created a sound short in the engine room. And this is what happens when he did that. Without the sound short, you got the black level, 12 kilohertz, your 12, 13 dB. By welding a bracket above and below, he defeated the sound silencing that was built into the ship and caused a significant degradation. So you can mess up your ships if you're not paying attention. So stay on top of those engineers. This is one of the Navy ships. In 1997, this was the fourth ship, and we had all these issues that we had gone out to fix. We'd fixed the fairings, we fixed all kinds of things, and we thought the fourth ship would be quiet. And we went out and this is a builder's trial, went out on delivery. And the top curve is what we had. We had 60 dB when it was supposed to be below 49 dB. And it didn't make sense. It was very speed dependent. And we did a lot of diagnostic testing. And I said that there's something going on underneath the ship. So before we came in, we had a team of divers come out to the ship and film the underhull. And it turned out that the paint across the acoustic window of the sonar was completely streaked like cottage cheese. And we did some investigation and found out that the shipyard painted the hull and they wanted to dry dock immediately. So they undocked with wet paint and transited at 12 knots for 6 hours. So it caused the paint to completely streak across the sonar. So I had the divers that were out full real time hand sand all the paint off, which caused a lot of headaches with the shipyard because then they needed to re-dry dock the ship to repaint it. But just by the divers hand sanding for an hour, we immediately tested again and the levels came back down. Now they didn't do a great job because it's not perfect, but you can see the impact with hand sanding the sonar. So we identified the problem. We knew it needed to be fixed. Now, the real downside to this problem is they had to go re-dry dock the ship, and they took it to a different dry dock. And that guy, the dry dock engineer, didn't realize that we had sonars on it, which stuck down lower than the hull. And he knocked over 11 keel blocks with the sonar and caused over $1 million in damage. So the shipyard caused $1 million in damage to a hull because they didn't let it sit and dry. And of course, the government ate it because they're self-insuring. But just let your paint dry. Let your paint dry. Here's some examples from the Healy. They had an EM-122. This is the screenshot of the swath of the sonar, and this is a good condition. This is everything's going pretty well. And then they have a boiler feed problem. So when you operate the boiler feed, you're getting all these holes in the data. And you can't really operate without the boiler feed, but it's a piping issue. They have a second problem. Just here in the middle, anytime the potable water pump kicked on, it caused significant impact on the sonar. You can see that a lot of data is getting dropped out when the potable water pump is running. These problems have been there for 25 years and never been fixed. In fact, when Kongsberg went out recently for an upgrade, they had problems and they were trying to figure out the problems, and they pulled out the 25-year-old report and identified the problems from that report. So, the Healy perhaps doesn't have quite as much attention to its data quality for its mission, but these are identified problems that could be fixed. Now I want to talk about transients and doors. On the Armstrong, there was a door that was, one level down from the main deck going into the auxiliary machinery room. And anytime somebody opened that door, the increase in the noise went from the blue to the red. 12 kilohertz, we were getting over 10 dB of noise. And you could hear it. You listened to it, it just sounded like a huge squeak. So we went down and greased the door, and the noise went away. We had the same problem on one of the TAG's Navy ships. We didn't know what this was. We got this data on the sonar, and that's huge, 65 dB. That's a huge amount of data in the EM-122. No, that was a 121 back in those days. We turned on our acoustic system, and first it sounded like a whale. We thought we had whales near us, but we realized that every time the ship rolled, the whale would make noise. Well, then that wasn't a whale. And so we went on our quest. We went walking around the ship to find out what was making the noise, and we got down to the level right above the sonar, and the door wasn't closed. And every time it would swing open, it would make the noise, and it would come back. So we closed the door. That's all we did. We closed the door. You came back up and take another set of data. That's how much and this was a non-watertight door that was just making noise. To give you an idea of how much that actually creates of impact on the sonar, with the door closed, at 11 kilometers, you're getting the green swath. With the door open, you're getting the red swath, just by not having a door closed. I'm not going to talk a lot about it, but this is the impacts of bubble sweep down. Everybody knows about bubble sweep down. It's a problem. Every ship has bubble sweep down. Every ship is talking about and eventually going to a gondola to push their sonars below the level of bubbles. But if you see something like this in your data, you have a bubble problem, and then you need to call 911 or something. The Revell has a new gondola. Thompson just has a gondola like today. It's going to be tested in a few weeks. I think you're talking about putting one on the Armstrong. It's not going to happen. Just go slow and turn around. Okay. But anyway, bubbles are an issue. It's been an issue forever. I'm getting close to the end of my examples. This is maintenance issues. The blue is a nice quiet ship at 7 knots. The red is when the ship's force decided to use needle guns to clean their hull when you're taking data. So the levels go from 40 dB up to 55 dB. To compare how much noise that is on this ship, the needle gun makes the same amount of noise as a ship does going 15 knots. Now you can't have them not maintain their hull, but sometimes when you're in sensitive missions that you really need a quiet environment, you might want to try to not schedule needle gun operations when you're taking your data. So in conclusion, design it quiet, build it quiet, but stay on top of your noise. And make sure your sonar operators and you guys, the technicians, are aware of what makes noise and stay involved in what's happening out there before missions. Take sonar data to make sure that things are quiet. Just pay attention to every ship has its own acoustic signature and everyone's going to be different. Just try to understand what's happening on your ship and it'll be better for everybody. So that's it. So any questions or discussions? Jules. She was first meeting.
You probably do talks like this and keep listening to whatever Tim might say. We had a UPS that was supposed to be a switching UPS, so even better than a cracking one. On the kilo one, and it was switching at 40 kilohertz, and it was driving the 38 kilohertz instrument and killing it with electrical noise. All these rumors that you hear, they're really worth following up.
Well, I want to follow that up. I keep coming to these things, yes, but listening to me, Tim's not going to be around much longer. It's retirement is looming. So we need a few good people to actually get more aggressive in understanding acoustics and actually providing the niche testing of these ships because my expertise is just acoustics. So I can jump from ship to ship to ship, but you guys have to really deal with everything on the ship. So it's hard for you to become an expert in acoustics, but it would be really nice if the UNOS community had a couple people that were really focused on keeping all of the ships quiet.
That was going to be my question. What is your succession plan? Because you have been saying that you're retiring for over a decade.
Well, I'm collecting Social Security next month, so things are truly happening. We have some succession. I have engaged another contractor to start tagging along on some things, and I'm engaging the MAC, which makes more sense for you guys to get more involved in the heavy acoustic work. And the Navy's helping, and right now the Navy's plan is to bring some MAC people on our next acoustic test on the Navy to kind of have them work side by side with me to allow them to understand what it is that I do on site, and maybe they can provide some of the expertise as well. Do you want to weigh in on that, Kevin? You got any? Okay. Mimi.
Hi, thank you for not using the OPS Explorer example. One, which was a miscommunication with the bridge.
That was a fathometer problem, yes.
Yes. Ship and put your equipment on, and ultimately the ship just had to turn off. It's extremely frustrating. So there's a human communication. So that was in 2011, and to start troubleshooting, we worked with our chief engineer to make a huge spreadsheet of things that we could start investigating. Is this the source of the noise? Is that the source of the noise? I think moving forward for ships, if somebody could help each ship have such a checklist to say, oh, we're starting to get noise. Here are the things that we need to check. Here are the people that we need to ask questions to. I think that's a good place to start. And then I don't know if you want to add anything to that, but I guess I have two questions. The other is, when you come on board and you put hydrophones around, can you describe, for the ships that don't have their own monitoring systems already, can you describe what you install?
Sure. First, your list sounds like a wonderful thing for the MAC committee to do. Ultimately, to have them have that kind of checklist. And if we get to the point, I can work with them to come up with things that I would check and have it be resident within the MAC boundaries. With regards to acoustic monitoring capabilities, what the bare minimum that I like to see is one hydrophone very close to the receiver array of the sonar, and maybe in the middle of the ship, if you have a 12 kilohertz, right in the middle, just forward or just after that transducer. And then you need a sensor, and it could be an internal vibration sensor over each propeller. So you want to monitor your propellers, and you want to monitor the noise that the receive array of the sonar is hearing. And that is very important, even if you only listen to it. Because listening to what the sonar hears, your ears are very accurate and capable of understanding what is happening. You can hear things coming on and going off. You can hear bubble transients. You can hear cavitation. If you have marine life that's degrading your systems, you can hear that. So just having a hydrophone there is perfect. You could, an amplifier like a stereo amplifier and a speaker that would provide great value. But if you want to take it one step further, you need the ability to do an FFT spectrum analyzer so that you can actually make frequency plots and look at the components of what the noise is. Now, all the new ships that are being built under the UNOLS, National Science Foundation, Navy, they're all getting acoustic monitoring systems. And if you already have the hydrophones, then the acoustic monitoring system, it probably costs $30K. It's not a lot of money, but some organizations, they would rather spend the $30K on something else. That's a decision that they just have to make.
Just kind of shout out to the MAC and some of the help that they've done for us. We haven't come out with this in our annual calibration cruises whenever they're available. We had one, this was last year on Rebel, and we ran our continuous BIS self noise test with again 712 it was, and we saw dramatic change in the baseline noise. So to keep a record, here that we've been noise a little like dramatic. So we started just shipyard trying to what was going on. Just happened to be at dinner with the captain and chief talking about their ballasting operations they've been conducting a couple hours earlier. So we reran the test and the ballasting not happening. We're like, good. So good to keep checking those things. All those different things make it.
In terms of noise reduction, would you say baffling versus dampening material, one versus the other, or a little of both?
Well, they're two totally different things. Dampening is what you put on the structure to dampen vibrations, which can radiate noise into the water. Baffling is actually a device that shields acoustic energy going from one spot to another. We use both. We use them in conjunction with each other. But you have to be careful with baffling because you don't want to baffle your signal. You don't want to put something that interrupts your signal getting into the water, but you can put materials around your systems that quiet. And then there's also absorption material, which is not the same as baffling, which actually will absorb the energy. Those are all three silencing mitigations, but typically you need like a naval architect or an acoustic engineer to actually help you design to put those things on a ship.
To follow up on all your guys' comments, ADCPs seem to back secondary to both of being what, as an ADCP manufacturer, real biased. You don't look at that. You guys look at that as at all in addition to what you do that's microphone surveys and stuff. Not mostly just focusing on multi-beam.
I do when I'm testing a new ship because we have to check every system on it. And we have acoustic criteria for all the ADCPs, just like we do for the multi-beams. Jules would smack me if we didn't. So, but yeah, we do what we can for now. The MAC stands for Multi-Beam Advisory Committee, so they might have to make some changes, but I can't imagine they wouldn't be able to look at ADCPs.
I guess mine is just more of a comment. I work on the RCRD program, and I was just Kate was asking if we have hydrophones on the CRBs, and we do have 5 self-placed hydrophones. There's 3 up by the sonar flag, so one forward of EM304 GX, one on either side of like the RX, kind of port starboard, one on the center board, and then one back by the Z drives. And then we also have noise consultations from J&A, and then I think the shipyard, they have their own noise consultants. And then during the shipbuilding process, they've come out and done different surveys and looked at like, the pump isolators and different fittings and different pipes. So yeah, it's building a new ship. You definitely have to take all these things into consideration. And then we have a number of different noise tests during stage 7 during the builder trials that they're also going to have to do.
And you also have the brand new noise acoustic monitoring system electronics.
Yes.
That can acquire data from all your hydrophones and show it real time.
Yep.
Cool. So it would be a quite valuable asset.
Testing. New coordinator now start. We are on the Healy, so we've been dealing a lot with some of those issues. And it kind of depends on the engineer officer how or they're interested in taking advantage of time to assess the noise. So I think next year we're doing some big changes. We're installing an EM304 and SPP29 during dry dock. And we had contour design and mounts for DT513 hydrophones at either end of all those acoustics casings. So at either end of the TX arrays, both the EM304 and for the SPP29, as well as port starboard on the RX array. And we're planning to purchase the NAMS system as well. And then we want to do a lot of drift testing with the engineer officer and just turn pumps on and off. And they can provide the data from FPCMS, and then we can correlate it with the hydrophone noise. So I look forward to engaging more on that topic with you.
Just remember, potable water and boiler feed pump are going to be your noise issues. So,
and also the oil or fuel oil pump on number 3 pieces that are.
Okay, I haven't evaluated, but I'm glad to see you're already up on it. So that's good. One more, or are we done?
Anyone upstairs? There's a microphone right there in the center. Just switch.
Okay. All right, Colleen.
I hear you laugh.
I hear Paul laughing actually, but yeah.
We can't exactly engineer the constant around your noise problems. So it is really, really critical, especially when you do any kind of upgrade. Whenever you come out of shipyard, if you move anything, if you change any of the machinery on the ship, to just spend a little bit of time to check these things out and make sure nothing has changed to make a new impact on your data. Anytime, I know that when your wait time is so hard, sea trials, there's always 900 things that you need to do. But the earlier you can do it, the more consistently you can do it with or without Mac there with you, the better chance you're going to have being able to collect records.
Well said. Thank you. Okay. Well, thank you very much for letting me talk.
So great time right now, everyone. We'll be back here at 11 o'clock. And don't forget, 12:45, the group picture. If you could please just see right out here in the front, everything will be guided to the right location. Yes, thank you. Okay. Keep going. Is there anything going? Okay. Okay, welcome back, everyone. We're going to go ahead and get started, and Marshall is going to present. Thank you very much. All yours.
Hi, good morning. I'm Marshall Swartz with Hui, and I'm here to talk about a recently revised presentation. If any of you were expecting troubleshooting CTD when the things go south, based upon the fact that Jeff had done a really stellar job at identifying troubleshooting methodologies, I decided to revise my presentation to incorporate some very new evolving events that happened in the last 2 days on the Atlantis, which is at sea right now, doing a whole line of deep stations at 3,000 meters. They're using a Seabird 9 1132 with a Seabird carousel. And I can't tell you all the configuration of the sensors that they're using on here, but what's pertinent was we've got one of our most experienced techs. This is Allison Heater. And as a side note, which might give you a clue as to how Allison gets things done, her background has been a fifth grade science teacher before she became a res tech. Isn't that right, Robbie? Yeah. And so whenever anything goes south, Allison just looks at you and say, sit down, we're going to take care of it. No baloney. But it's wonderful having people with experience. We have all kinds of people out there, whether they've got a year or 20. We value having the input and the participation of the techs who are open-minded and trying things out. And I was particularly thrilled that I got a hold of this information by one of my colleagues while I was flying out here. Some of you may know him, Dan Finari. And, if anybody's going to get a hold of a person in the air, it's going to be Dan. So Ken knows that well. Anyway, it's get a hold of Atlantis right away. And the issue had to do with they doing work, and all of a sudden they've started throwing errors shown by the red light on the Seabird 11 deck unit, which is just on depending upon the version. The 11 shows either a error or I think a data error, depending on the version, but it doesn't give you much diagnostic. I thought this was a great opportunity to capture what they identified, what they did to work through the various options that it could be, how they reached out, and what's happened since. So I just want to thank at the beginning to the comments by John Calderwood, as well as the Seabird team. John responded 3 minutes after I did with a very comprehensive and parallel, but more specific suggestion path. And Chris Cheshire and Dave Stalkey with Connor Bacon had formulated several things to do. I realized there were some items that most of our techs may not be aware of data that's available in the CSAVE default directories for doing diagnostics of transactions that are occurring between CSAVE and the external instruments on serial control that usually aren't something that most techs don't even know where it is or what it is. But you'll see in this presentation, an example of this will tell us a lot more definitive information, and hopefully it'll be something to be aware of for you. And then with the time we have available, there were some questions that people had about some general matters on CTD operations, ship operations, configuration, what have you. I'd be glad to handle that in the time we have left, if any. I'm sure there will be because you'll get bored with this, but some people had talked with me in a few minutes yesterday and just asked them, how do you do this? Or what's the time you keep the CTD in for soap? What's the principles behind it? We're not going to solve those matters here, but I would like to engender a discussion for these things that techs are interested in, because we often encounter that with our scientists. So let me see, how am I going to get there? There we go. This is what I faced. Basically a help. I'm on the cruise right now, trouble with the deck unit. And she's coaches it. You see, I think that's what it is. We had comms, they were doing stations. They started up and immediately ran into problems. And she realized what can happen when they have a bad cable or a sensor that's failed, that you can fry a lot of things if you leave it powered up. So She mentions here, try starting a new file, nothing worked, fired manually, came up. She disconnected everything. She still found that when they got it up on deck, they tried it. They're testing the wire in the drum. So far looks good. What do I do? She called Seabird. She didn't get a response. I'll point out that Chris Cheshire jumped right on this. And as soon as he was aware of it, I'm pleased to say that while Seabird's gone through a lot of transitions, they are aware that there's a responsiveness question in the minds of a lot of users about how can we get a hold of somebody now? Because if we get that voicemail, who will answer? Um, I've often been the repository of those backups, and I can say that it has gotten better from my perspective, but I shouldn't say that everybody's satisfied. Chris is aware of that. The whole team is working on that, and I give them a lot of credit for that. So here were the points that we can take out of that. They have present cruise going on. She thinks it's trouble with the deck unit, but remains open-minded. Still had comms, but couldn't fire the bottle. So that would suggest it wasn't a dead fault. They tried starting a new file, etc. Nothing worked, came up. Then it was the red arrow light continuously red when powered up. Couldn't even make the connection. Continued in deck, tested the wire. So she divided and conquered. She removed the C cable connection from the question, used a bypass cable, deck unit right to the Seabird 9, so that you take the slip rings, the lab lead in, and the C cable out of the equation for consideration. Still had that problem. So said the fuse is good, getting the voltage. And I asked her about whether they saw what that red light means. Couldn't find it in the manual. The Seabird manuals, depending upon your version, are very dense. They can't possibly index everything. Some of this information is rather obscure. So I thought I'd just bring out a couple of these points. The first follow-up came out within 2 hours. I was able to sit down and compose a few things. This is what I sent them. Wanted to know the serial numbers of those units. So Seabird knows which versions and configurations. At Hui, we're not using serial data uplink CTDs. So we don't have that unusual telemetry configuration, unusual for us, that is more prone to disruption. There's a clip below that comes from, and I referenced the manual. This was the only item in the manual that said anything about the LED for error. Error LED flashes when data is incorrect. That is, module indicates a skip scan. Well, what does that mean? Does anybody know what that means or how that happens? Has anybody had any experience with that? That's why I wanted to bring this up, because I think these are pertinent items to walk down the path, say, okay, this is what's happening. What do I do about that error? And I would love to see Seabird try to bring that to the fore in support of our people that see. So I wrote, seems to be telemetry. Well, that's pretty obvious. I'm glad she brought it up. And I really give credit to our techs. Most of them, if not all, will go out of their way to take time and say, the last damn thing they want to do is sit down there and compose an email to answer Marshall or Robbie asking a question. They do it. And you'll see more information from her on this. Now, this is what John responded 2 minutes after I had. He goes in to specify exactly what that means. And I won't walk through this. You can see it in the presentation packet if you'd like. But as he points out, if the error is on, the data stream's not being received properly. He mentioned the various options, either a damaged modem, which we have seen at Hui. We've had damage to the modem component of the internal circuit board of Seabird 9. Not clear why. Our units are not brand new in general. Some of them are very old, but they've been workhorses. She's checked the fuses, those things that are simple. He does mention that try connecting a spare CTD to eliminate the CTD at fault and so forth. So he hadn't seen any more than that original email. And I thank John for taking the time to respond. That's what UNOLS is about. RVTEC is about, because we're all in this together when we're out there. And I can say that if I've ever reached out, people will stop, pick up the phone, email, wherever they are, and say, have you tried this? And that's what I'd like to continue to encourage, because that's the reason I've been able to get stuff done. And I hope people can continue to do that. So John had mentioned lean store to damaged C cable, rather consistent with what we've seen. So I followed up then and just mentioned a rather obscure thing that's not in the most Seabird manuals, but that I wanted to make sure, because Allison was just reminded of this when Robbie had talked with her about this little file set that exists when one is running CSAVE on a machine. It exists into the default, it's the app data file or the app folder where the CSAVE software is resident. It's called an SA text.log and an SS text.log. These two files contain all the transactions, the handshaking, human readable references of what those modules are trying to do. The first one, the SA.log, is the acquisition module. Many of you may be aware that Seabird software presently is consisting of, in the CSAVE versions, of an acquisition module and a presentation module. And each of those are generating a chronologically appended log file that's never overwritten. It's just appended. And sometimes if this goes on, I've been on a ship one time, we found 5 years of data on one file. They're not huge, but you can go back and find the exact date and time, the transaction, and a human readable response that may help you diagnose things. So Allison had picked that up for us. So Allison wrote back and said, gee, we got this working. And she later tells us exactly what she did. But she did try plugging the deck unit, the 9, directly into the carousel, and it worked. So they changed out the carousel water and the associated cables. So she said, confused by the fact we had a constant red error light. I will say that this story does not have a definitive one source of error solution. We just don't know. But Allison's done her best consistent with the available time and the fact that it is running and operating properly for them, at least as of this morning, that she got things going again on these long and chronological or time-dependent stations that they're running. So I was pleased to see Chris had gotten back and said that he thought that her troubleshooting approach was good. And, that gives her some confidence they're on the right track. Here is the snippet of Chris's email, which was 7 hours after receiving this. And he points out, gee, we're available to assist now and the rest of the evening, whatever it's going to take. She asked for a cable diagram and got that. I won't go through all the details here, but did give an explanation of what the red error light means. This can happen in a number of instances, and you'll see in a little bit some of those markers as to what those instances may be. But he goes on to mention it might be worth inspecting internal shorts bulkhead or in the Seabird 11 plus deck unit. Sometimes things get pounded, years of operation in a rack, something can come loose. It can also be within the Seabird 9. It can be within the pylon. It can be the external connection to the bulkhead connectors. So the second part of his email continues on. There's a telemetry problem between the 9 and the 11. So as he points out, when it's multiplexed and there's a multiplex failure, that's what triggers the red light. And in general, the data will be inconsistent or stops operating. And then he points out the common problems. I underlined several of those: terminations, connector corrosion, C cable or slip ring, electronic problems, and so forth. Unfortunately, they don't have a spare pylon out there at this time. But I'm sorry, they don't have a spare deck unit. They have the spare pylon. Nonetheless, Allison was able to do that check. They realized it wasn't the pylon. They have one additional information or observation, but he did point out an experience they had where a minor seawater leak into one of the dummy plugs of the pylon. So this would be a pylon that has a serial data interface. It's a Seabird 32 or the Seabird pylon. I believe it's option 1D, where you have 3 connectors on there, and 2 of them are hot. It enables you to plug the C cable directly into the pylon. and then operate the Seabird 9 or Seabird 25 as an ancillary instrument to the pylon. That's typically not done with Seabird 9, but it can be. Nonetheless, it presents a risk because there are additional connectors that could get wet. So it points out to good data hygiene or good hygiene practices in the maintenance of our connectors. I'll speak a little bit to that near the end, but it's so fundamental to what we do. And there are various philosophies about how one cleans, inspects, turns around, or reinstalls dummies and so forth that may actually be something to reconsider. Let's just leave it at that. At least if we're aware that can be there, that can be an issue there, then we're on the right track. So he did point out that they were troubleshooting a 19 plus after much testing. We found that the 6-pin connector on the 32, which was not used, so that says they were using this with the 19. Minor sign of exposure, but notice he said tiny white and blue spots of surface oxidation, which were easy to clean. That alone seemed to cause the entire systemic telemetry errors. They cleaned, dried, lubricated it. It's working. So again, if any of us are trying to do this on a wet deck, you just have to be so careful. And we can't avoid working on wet decks most of the time. But the more we're attentive to that, ask for help from somebody, the better off we can expect the results to be, or at least a shortened timeline to getting back in action. So what I wanted to highlight were that this reply came from Allison yesterday. She did say it's complicated by strange symptoms from the deck unit. So she mentioned that she recovered it. Underwater unit air was constantly red. She calls it underwater unit air. It's the deck unit indicating on the red light that's second from the left of the band of 6 lights on the front panel. And only the deck unit plugged in with no other instrumentation. Underwater unit remained red. Got an alarm. Again, deck unit had no connection with the 9. Seabird found this unusual, might have something additional, but the light did clear. So that remains unanswered at this time. But she points out Allison worked on the deck unit a while before attaching it directly to the 9. What they have is I've encouraged our techs at Hui to have a bypass cable. So you plug one end of the, the MS3S 3026 plug, goes directly to a 50-meter cable and to an MCIL2F to allow you to connect right to the Seabird 9. You bypass everything between the deck unit and the CTD to take the entire C cable, slip rings, lab lead in out of the equation. If you did that, plug the carousel in, error reappeared, so they changed the carousel. She did say if we carried a spare deck unit, I would have been spared the troubleshooting extra time. But she also mentions they had some other leakage issues. Now, I've not heard more about this. I don't think it's directly pertinent to what they experienced, but she did say it may have been related to the carousel leaking. They had some science instruments on. They had leaking there. Quite certain they definitively had a cable leaking, I should say, and that's a cable between that sensor and the Seabird 9. So she mentions one of the things they did. They had communication issues with the carousel. They proceeded to do 50 casts, no issue. I feel quite certain we had 2 problems brewing, and I'm hoping the deck unit still isn't a third. So she's pointing out she's still not confident they've beaten down all the issues. But this is what I really encourage our techs to say. I want to know if they're confident or just feeling there's something else that's nagging that hasn't been resolved. This is a clip of the 2 files she sent. This file is, I think it came to be, about 26K. It's just a text file. This one goes back about 3 months because they clear these off now. But you can see it's chronological from the top down, and it begins at the first entry for this station. When this starts up, you'll see it says where that data is going to go. This is the acquisition software module telling us CSAFE started. This is where the temp file is going. It read the XML successfully. So this is where you're going to find if you have an XML file problem, this will show up that it can't find the XML file or can't read it for some reason. As we go down there, we see that it's generating these two temp files. I can't tell you what that temp file is. That's a question in the future for Chris and others. Again, this is not something most people even know exists, but it's on every version of CSAVE, I think since about 2006. And if you have an issue, I would urge you to look at the data path directory. You'll see at the very top, Science App Data Local, Seabird, CSAVE, and you'll find these two files. This one started successfully up through start data acquisition, communicated, but it did say, I failed to get the advanced values from the 11. That did not stop this from operating. Robbie. Okay. Thank you. Yeah, please bring that up. They initialized the water sampler correctly. There was a bottle reset. Notice this is all happening in a matter of 5 seconds. Initialized an MEA, and then you'll see there is a break here that looks like there has been a break in the communication, and the system that was just acquiring and logging the SA log file hiccuped. So the second half of that, so this is at 15:54:36. Waiting for data, acquiring, it's archiving. And we go down here now, it skips forward 1 hour and 3 minutes. They're coming back, fire next bottle, unsupported modem message. So that's what's helpful for Seabird Diagnostics, is saying, gee, I can't understand what's coming back from us. It doesn't tell us specifically what the message should have been. I did not include a sample of what it should look like. I can provide that if you'd like, but eventually at 16:58:53, down below the second highlighted yellow area, you'll see stop data acquisition. So basically, Allison pulled the plug. So I'm not going to waste my time anymore. And she came up to 2,000 meters, as she mentioned in the email. Shut down. It did receive the shutdown. So even though the data path, the data acquisition module had croaked, it couldn't proceed further in acquiring data. It was still telling us what's going on. So let me head over here, and this is the SA log. I'm sorry, this is the SS log is the CSAVE log. That's the presentation layer. That's what's giving us the graphics, the control and command. The SA log is the acquisition. So that's the workhorse that's turning the crank, telling us how to open the port, what the configurations are, and monitors what's expected to be coming in. So again, we have the date and time, and look down here where the red mark is. You'll see just before it, it's opened up COM2, open up COM4, everything as it should be. COM2 is the modem communication. COM4 is the 4800 data rate coming in for the CTD, unidirectional data uplink, or universal data coming up to the Seabird deck unit. And you immediately get at the same time, well, it's the same because it's timestamped the same, with 3 messages from the carousel that it just didn't make sense. So it reset, and it actually timed out and reset. Then that time took approximately 0.4 seconds, reset and shut down. So that's the extent of the logging of the software for diagnostics when there's a failure. If that had been running, this area between, for example, the red arrow and down to the data acquisitions, I believe, yeah, right about here on the data acquisition thread, that would not be there. There are typically 8 lines of information just on the regular turnaround of a station during its life cycle, including through shutdown. So are there any questions about this or anything you'd like to ask or know at this time? I'm going to endeavor to follow up with Seabird. I've sent this presentation to Chris Cheshire. Maria Luna has a copy of that. The people there at Seabird are going to work with me to try to address in this particular situation whether there's anything further they might recommend. In my opinion, Allison handled that really well. And I wanted to point out the takeaways that we have from my experience with this and her experience. So pleasantly, instead of stewing about and wondering, what can I do? What am I turning around here? What stones am I looking under? Allison reached out nearly right away and said, here's what's happening. I can take care of some of the diagnostics on my own while these people are thinking about it. And so they reached out and they had an open kimono approach and say, gee, I may not know everything. What do you think? And they looked at the entire end-to-end package, whether it was the C cable, whether it was the sensors that were external to the Seabird 9. Is it the pylon? Is it the interconnect cables? What is it? Could be the deck unit too. It could be some way we're configuring the deck unit, although unlikely, but who knows if you've had some fault in the software that may have driven some issue to change it. Doubtful, but SSGs kept us informed continuously on this as best as they could. And again, what you saw in Allison's email, she thinks there may be multiple causes. So they can't be confident that won't happen again. It's unlikely at this point for them, but we'll find out. So what I'd like to ask of you is if anybody has experienced this kind of event where you've got something uncertain, you said, geez, I've realized that yesterday I saw this wet connector and we knew it was giving data problems for the conductivity cell and the second conductivity, and we cleaned it and it's working. That may or may not show up here, depending upon the amount of current draw that has. When you've got sufficient seawater bypass between pins 1 and 2 or 1 and 3, you can get enough current, you can draw down the bus voltage and cause failures to telemetry. That's why these things can be rather obscure, and to find that there is a means where you might be able to see some channels going. And of course, you combine that with your ability to use Seabird acquisition or data processing, depending on where this is, to observe in a time domain what's been happening. I'm not going to go into how you do that. You all know it. But keep an open mind, because what looks like it's obviously a problem in the C cable may or may not be. So given that Jeff's presentation yesterday covered a lot of the methodologies, I was not going to rehash that, but I wanted to bring up this because we couldn't have planned it better. So to have this happen and to see that they were able to go through and exercise the system, ask help, and they got it from Seabird and from others who had contributed. And I really thank John for that. Several others may have reached out to her directly. I don't know, but they're busy and they're doing what they need to be doing. And I'm really pleased about that. So given your own experiences, do you have any thoughts on this? Any things you'd like to see? Maria's here from Seabird, and she would be, we're recording this right now, but she would be a person who can take back those messages and say, gee, here are the things we are hearing at RVTEC are of interest. Sorry, I didn't mean to put you in the hot spot, Maria, but you're up next, by the way. Yes, Robin. Yeah.
I don't want to dominate the room.
Sure.
Let's see. So there have been a couple things coming up over time that I think may interest everybody. The newer connectors that keep getting sort of vague feedback that suggests that they're not working perfectly, and I think they're not being seeded properly. So you're getting comments that one comment is that the shell, the retainer is not holding them, and I would point out that that's not what that is for. That's just to prevent yanking them out. I've also had cases where somebody's mentioned that they got it together, it looked good, and then looked at it an hour later and it had spread apart by like 1/8 of an inch, which certainly indicates there is some air compressed in there. So it's possible these are not working as well as we had hoped, but
yeah,
we have more going with them. It's certainly easier to get on and off than those other ones.
Yeah, I have a lot of experience in that, as you do. In my scope of work up through my retirement a year ago, I've had experience with Jason and Alvin work with our buddies at uh, communicating with both Teledyne, Seacon, and Ray Esteban at Teledyne was going to be here. I'm sorry he can't make it. He's a very open-minded guy. He's a sales engineer. He's there. There's Ray. Hi, Ray. I gave you credit. But Ray has been long-time presence there and has been very valuable when we brought up issues. Similarly with Subcon, where we're using Subcon connectors. To your point, Robbie, about the gap that can happen, people have noticed that if you have a micrometer on the length of the barrel of a, for instance, an MCIL series connector, you may see some variations in those. And I might point out if you're using connectors that are not the Teledyne or Subcons, and they do not recommend intermixing them. My experience has been most of the Subcons will work very well with the Teledyne Impulse, MCBHs, and so forth, but no manufacturer would ever guarantee that. I'll simply say that during the transitions of manufacturing sites and so forth, in some manufacturers, that's been erratic. I'll also point out that Seabird has, on occasion, been sourcing some of the connectors locally. I don't know if you can address that, Maria, but that I was told that there have been some connectors or dummies that have been made locally because of the unavailability of these. I don't know if this applies to the MCBH or the MCILs or MCBHs, the dummies with them. But that's something to be aware of. Know your connectors, know what to do, know how to lube them. And I can say that some of the demonstration videos about, for example, how much lubrication to put in a female MCIL is quite variable. I don't subscribe to filling it a quarter or half the way because there will be enough trapped air that it can pop back out. So I generally take a little more conservative approach, but make sure that I've reseated twice to 3 times. And then, in the process, if I have to approach the connector and say, I don't know what that status is, I'll carefully pull it out, observe if there's any water. Typically, you're going to have some moisture, assuming you've dried off the barrel of the connector once you've removed the locking sleeve. But if there's water or any popping sound to that, you might suspect there could be some entrapment. Nonetheless, on critical missions, which basically all are, we recommend, but we can't practice, every removal of a connector warrants a cleaning and a reinsertion. So it depends on the value of what you're doing. But the manufacturers provide some guidance on that. And I think it's wise to ask the manufacturer if they have any questions. Rob?
Since you it's my presentation, thank you. As someone who doesn't know anything about CTDs, but knows a lot about troubleshooting, I wanted to point out something in your log files that I thought was interesting.
Yeah.
And this comes down to information that you're getting. Can you go one forward?
Sure.
Those ones might be also helpful, but what's interesting here is you're getting hexadecimal codes that are part of the message. And just from an observation perspective, those F messages usually represent some numerical form of like all zeros or all 255s. It's almost like a flat line of information. And what I would be curious about is what the ordering of those 2 hexadecimal codes in that message are, because it's almost saying like, I got nothing, it's unsupported, and it's referencing 062D06, which probably references some memory location or something in the physical device. And that would be relevant to the higher level diagnostics of figuring out where the actual fault is. But hopefully, since I know nothing of CTDs, I didn't say anything stupid.
No, it's not stupid. I can't speak to the hexadecimal 4 bytes that are there, the FF, so that's 255. But my guess is that there is some response on it on situations where, for example, the third line here, if that is getting that code 1A, it's going to know that what's going to follow incorporates some amount of data. I don't know how to read these. There's no document that I'm aware of other than some internal Seabird documentation that would help that. But that's a good question for Seabird. But you can see on here this unsupported modem message shows that. I think, yeah, we have again on the previous page at 155434, the fail to get connectivity advanced. So not quite sure here again, but you'll see that there's an F6 code at the end in the first byte. So good to point that out. There may be more in there than we know. Thank you, Jeff.
Marshall, I think what we have here, well, let me back up a little bit. So I find these things CTDs drive me bananas when they fail because the channel that seems to be messed up is never the problem. Over and over again, this has tripped me up. The best one is when the configuration file resets itself and it tells you that there's no GPS, and that is not the problem. So I don't know how many people have experienced that, but if you set your system up to the factory defaults for your serial ports, that problem just vanishes because then when it resets itself, it's still on the right ports. But well, let me knock off this conductivity advanced value. So our system is the older system, Mark. I think we just have an 11 plus.
I think they're all 11 pluses, but could be.
Believe we have.
Yes, yeah, that's an early generation 11 plus. Yeah. 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 Thank you. You're right. Thank you for pointing that out because it can't get anything from a deck unit. That's why I asked for the serial number.
And I've known about this. Maybe sort of known about it more for the last years. And I feel like I'm just kicking myself that first thing I did read these two files because it's crystal clear in this, doing it on a regular basis, that there's something wrong with the carousel. You look at the file, no carousel. Not what we're getting on deck and any of the other messages.
Yeah.
It's on, the message says that there's a modulo error. So I would strongly suggest if we all start reading these files, I think our lives will be much simpler.
If I may, thanks, Robbie. If I may add to that as a action item, I would recommend Seabird look at whatever they can do to provide us more guidance with specificity on that, because these software modules have grown and grown and grown. I hate to think of the number of people, our man hours have been taken just maintaining what they've got, and it's now been stale at 6 years or so. And I know there's new software that may come out in Seabird soon that will be a complete rewrite of the presentation, acquisition, and the data processing side. So none of this will be reused. Hopefully, we'll have similar indicators that give us pointers to what may be going south. So I think that's a really essential point because to Robbie's issue, we have an inconsistent level of error definition. And some things might point right to it, especially if we know by experience what they may be. Others may just say, well, it could be somewhere in that channel, but if you know the architecture of the Seabird 11 and 9 when interconnected with the pylon, then you might think, okay, this data is transiting here. It's not getting there. Software saying, throw an error, mark it, move on. And as you saw, in some cases, it can still move on just to close out gracefully. But it's a difficult to maintain software package for sure. And that's part of the reason they're rewriting it, because probably is best said, it's unmaintainable now. I'm sorry, go ahead.
The topic of this troubleshooting through this. We were out to sea and we're using a Seabird 32 and there was a lot of complexity. The PI was putting together all the connections between machines and ran into failure. Wasn't communicating, wasn't anything. if you're familiar with 32, there's all kinds of lights with balls of fire, and those things were just going on sequence, even when it wasn't plugged into the C cable. There's all these lights going on.
This is Seabird 33, 36, or 33, maybe. Yeah.
Yeah. So we were figure out what's going on. We did the same kind of started isolating aspects of it and direct plug in and things like that. So it worked directly plugged in, so we started breaking it down. I guess it's a long story, but at the end of the day, sometimes the simplest thing can take 8 hours of work. So these things are great to get into the complexities of like maybe water or machines and things, but don't forget about polarity. And there is no, like on a lot of modern electronics nowadays, you plug stuff in if the polarity is wrong, as a polarity rate. Something like that would be epic to have, because we didn't have any idea. And we were looking for all the files and resetting and all this stuff, but at the end of the day, it was just reverse polarity. And that's the thing we didn't do. And it took it like 8 hours. Sounds silly, but what I'm trying to get at is fun. It's just
Sure. That's a very good point. And I know Seabird Engineering has been working toward providing reverse polarity protection for newer gear. That doesn't exist in everything. And I've had some experience with 33 for years. My experience has been when something goes south, when some noise, let's say some moisture got between the C cable ground and hot signal line, the noise would trigger the sensing software or sensing firmware in the 33 to think it's getting trigger receipt. And that's why my lines were going off. So you'd see these bottles lighting up when I didn't fire anything. I've seen exactly that. It's a known issue. But there again, you think, wow, what's happening here? I might point out that I started 49 years ago in this business. I was privileged to work with the fellow who invented the first CTDs, Neil Brown, who worked at Hui. And he had designed the first deck units with a speaker in them because he knew if you could hear erratic noise on that speaker, then you might have a good indication you've got some kind of an erratic connection, whether it be the slip ring, moisture in the connection, or some variable load. Similarly, those deck units later had a milliammeter, so you knew how much current was going down the cable. It wasn't simply in line with it, because connecting a DC milliammeter in line in series with the deck unit will mean you're not going to get the telemetry through. But it was right there where the power supply provides the feed through a choke. And those two things were instrumental so many times in the 70s and 80s when we were doing work with that gear. Those have long since been removed. I actually took it on I've worked with another engineer right now, and we're going to modify an older cable connection harness for a Seabird 11 to just try that. So we'd have an inline milliammeter and a speaker, so you could hear this and see if we can correlate that. It sounds ridiculous, but it was such an easy definition. Say, somewhere I got moisture in that C cable, because you won't hear the crackling if it's moisture in the downstream connection from the power supply, the Seabird 9 or the 25 or the 19 plus online, cooking off with an external sensor. Yes.
Yeah. Marshall, my name is Chris. I'm with Telling Pulse, and nice to finally meet you in person, Marshall.
Nice to meet you, Ray.
I've been working on we've seen everything as far as connector wise, cable. And what piggyback on what Marshall said, I mean, for good practice is to have similar company connectors and cables, just to be on the safe side. We don't know how Subcon is maintaining their tooling, how they're testing it, so we have no control over that. So whenever something calls me, we always make sure they have both Teledyne connectors and cables. And as far as maintenance, I think what you're saying, Marshall, is correct. Yes, we do lubricate and everything else, make sure all are set inside. What we want to also reiterate is like, grease is fine on these, like, so you want to trap air, like you said, but not too much because that could trap air. It could also, it acts like a sticky film, so it'll trap debris once you get there. They don't stay there. So I've seen shorting like that. You go inside, oh, there's a bunch of just crap in there that needs to be cleaned out. And so yeah, so it's fun to just reiterate that and like I said, I'll be here the rest of the day. So any questions about cables and connectors, I can certainly
Thank you, Ray.
yes.
Question for you. So if you don't like the grease that much, what do you recommend?
Sorry, was that?
What would you use as an alternative to the grease?
So we recommend like silicone spray. So, and that is, we have a 3M silicone spray that I give you a bottle number and just spray it. They have inside the sockets. There's some silicone spray that comes with a, like a straw catch. You just spray it, and clean everything out. So yeah, sorry. Yeah, kind of clean out whatever's inside, and then you go on pants and stop it. Sure. Yeah. Yeah.
Ray, I'd like to ask a real quick question. With regard to the connectors, my experience has been that we can experience carbonizing of the surface of the rubber at voltages at 30 volts or more. So what you get is a conductive track formed by the seawater bridging, especially in the MCBHs, bridging between the sockets or on the MCILs to a lesser degree up the sleeves on the pins. But once you get over 32 volts, you can be prone to carbonizing of a track. You'll see that especially on the J1 connection for the C cables, for the Seabird 9 and 39 and 25s, and not very common in the connections to our sensors because they're only supplied voltage at up to 15 volts. But a carbonized track can be easy to miss. And when you have it, that thing will progress very quickly. And the carbonizing occurs because the neoprene's breaking down under the heating of the steam of that current flow. And if anybody has worked with the Jason guys and Alvin, you can see that a lot in some of the higher voltage connections. That just means you have to remove that connector. And I want to say a shout out again to Ray. We had a case where we wanted to outfit a Seabird 32 or Seabird pylon that was originally set up for the 3 connector configuration. Wanted to remove 2 of the connectors. Well, it turned out that that's a very hard dummy to find. So it's a blind plug that will replace an MCBH. And it's this 1/2 20 as used in Seabird systems, not the 7/16, which is standard. So if you're buying replacement connectors, know that base for Seabird equipment is almost always a 1/2 20. Ray fortunately looked back through the records and found they had provided some to Seabird, and we were able to buy some from Seabird. And the benefit of that is if we're out there on a long cruise in the Southern Ocean and we happen to have, let's say, one of the J2, J3, J5, J4, I'm sorry, J2, J3, J5, J6 on a Seabird 9, which are the analog inputs. Let's say one of those connectors gets damaged or smashed. You may not have anything to replace it, but you could probably operate without it. So we asked and they provided the link. They provided me a lead. We contacted Seabird. Seabird sold us 4 of those dummies. So we could replace some of the connectors should we have a problem with the instrument at sea. And we don't want to pull it out of service because one connector is bad. But those are the kind of options to start thinking about from maintainability standpoint. And they were only available on a special order production from Teledyne, and Seabird was kind enough to say, we have enough to provide that for you. And that was great service all around. Thanks again for your digging that out, because nobody else knew what that was. Okay, any other questions this time with regard to this, or Robbie?
Comment on. So. Sequences. And says, so for diagnostics, like for instance, if it immediately screams, fuse is blown. And for reasons that are mystery to me, if you have the cable connected and the fuse is good, but the CTD is disconnected, which seems like the same thing wiring wise, it doesn't scream. Apparently the capacitance of the cable is enough to make the deck box happy. And this came up yesterday because Alvin was asking, what is the box supposed to do in the situation she was in? And I realized I didn't have that particular scenario memorized. It's like I have to sit down and try them along, write them down or something. And then the other one is once you see it start up, there's a sort of a sequence to lights that you just watch them, you'll know it's right. Kind of a widdly move, widdly move, widdly move that it goes through as the lights all blink around. And I just find that one interesting because if I'm in a hurry, it takes like 5 minutes. I'm just doing a regular task. I know that's what I do to sort of see that things are going through.
Thanks, Robbie. Any other questions about this or Seabird or CTD related matter? C cable? Yes.
On our ROVs in Bahrain, we have some specialized 19s that we short. They don't have the batteries.
Yep.
Got like 4 of them.
19 short case. Yep.
At any given time, like 2 out of the 4 ground faulted. In turn, like we have ground fault indicators built into the ROV, and like they're just consistently trying to eat dog. And we've like tracked it down to to the point where we took the whole thing apart and found that we just had like a straight, like one of the pins of the bulkhead connector is shorted. And,
wow.
And a lot of times this doesn't appear until we're like, 500 meters down or something. And it's been like a continual issue of like these things just want the ground fault. There's it's like a small capacitor or something attached to the bulkhead connectors that can fail, that can cause a similar problem. Just seems like there's a lot of ways like ground fault. I wonder if anybody had the same issue, or if anybody's even looking for ground faults to have CTDs attached to other things.
Yeah, I can address a bit of that. Recently, we, for the very first time, provided Alvin with a Seabird 19 for direct connection through the hull. They have never done that. They've always required it to bring its own power. And that really took a cadre of several engineers and others to make sure it was qualified and met the standards. But the Seabird 19 plus short case we had, what that is basically a titanium, ours are titanium cases with just one end with connectors and the head on it. The back end is it's a blank. There's no blank, just a hole, and a tank, so to speak. But early on, we had a similar issue. We never did track that down, but we sent it back to Seabird. They sorted it out. Did you communicate with Seabird at all about that? And what did they say about the connectors?
I think it's been like, I think 10 years.
Okay.
Got totally under control. But like we sent it back, and the first time it was just like, they're just like, there's nothing wrong with this. What are you talking about? Then we talked to, I think we talked to Chris. I've talked to Chris about it a little bit. We need to, we have a unit that we're about to send back that's ground fault. Can't get a ground fault on deck. So I think I'm just going to send it back, and I think that the main problem is with the bulkhead connectors. So we're just going to have to replace all the bulkhead connectors. Because like what it was with the initial one that we really tracked down was just having a bulkhead connector. And that was like a problem with 2 of them. So like 2 separate units had just a shorting bulkhead connector. It doesn't affect the operation of the CTD at all. It's just you know, putting 24 volts
Mhm.
into our RV, which we don't like.
Yeah, I know in the past, Seabird has had some vendor specific problems in certain batches. And there is not 100%, correct me if I'm wrong on this, Murray, but there's not 100% incoming electrical inspection for high pot and so forth, or at least there hadn't been in the past. Not that that would detect that, but we did dissect one connector, I remember, that was going to be used on Nereus years ago, and there's a name from the past. And we had a similar failure, and we took it apart and found that there was a molding void with a strand that had come off during the fabrication and was just so close to the shell. And that's something that you won't detect. I don't know of any reliable way to quantitatively evaluate that kind of condition. But it it caused a problem eventually when somebody was removing the connector from that MCBH, and it bent it just enough. Let me take that opportunity to point out one of the simplest things we see that's avoidable is short radius bends. The manufacturers may or may not provide you a specification. CCON used to have specifications stamped right on the wire that said minimum bend radius of 3 inches, for example. We'd see that on Sentry all the time on those cables. And you had to follow that, because if you bend it more than that, you have the option or opportunity to fracture the braze point or to cause damage to the insulation. And many times I've seen people prepare a Seabird 9, or in dressing the wires, they're just tightening those tie wraps so tightly that they've got a loop like this. And the wire should never be handled like that, nor should it ever have a case where you bend it right at the connector's mold head, because that's where you're going to get the strain. That's not typically covered in the manuals, but I'd say it's a common sense point to bring up and emphasize with anyone handling your cables. Have anything to add on that, Ray? Where's the mic? There you go.
Well, it is to detect some of those small areas, because yes, because there's between a rubber and a conductor, there could be just small film that normally detects that. We don't 100% pressure test each connector when we are HUL sample, but there's always sometimes there's just too many wires. I don't want to think too many wires, but the bundle of wires could stray off a little wire, you know, because you're doing with a high pressure molded connector. It's molded machine, wires, and then it basically pressure molds the rubber around that connector. So there's connectors move around, there's work, there's wires move around. It's like, yeah, it's one of the issues. What do you will try to find during the quality control? They look at the surface and everything else, and hopefully find, you know, whatever the manufacturer is, they may have this that one. And yes, there is areas that we cannot. There's voids. You're taking void in there that could happen.
Yes, I think, I don't know what that number was, but for instance, the MCIL 8F is an epic example of that, because of the sheer number of cable. You got 8, what is it, 8 or 24, 22 gauge wires coming into that assembly head and then molding around it. So the proportion of mold volume to wire volume is fairly low.
Well, real estate, because you female connector, female sockets in the mold, and you have wires, sockets and female sockets, and you have very little real estate inside, you know, inside the rubber as well.
Thank you. Any other questions, or it's just about lunchtime?
Did anybody have any? We can, you know, approach you later.
Sure, anytime. You know how to reach me. Thank you.
Stick around for the group photo, Sarah.
Nice door.